First,
Now I
is he ready?
Dr. K.K. Nanda.
First ask Dr.
Yes.
Nanda, is he ready?
That's a good question. Is Dr. Nanda ready to?
Dr. K.K. Nanda is here.
Yes, I'm ready.
Yeah, that's great. That's great, Dr. Nanda. You will be the first speaker because we had a problem connecting the previous speakers. Now, before we start the day 2 lecture, I would like to welcome you all. Thank you once again for giving us so much of encouragement and having participated in such a large number. I again reiterate that these deliberations are primarily for the students, and since increasingly our science is becoming complex, we are unable to reach to the students, master level or even researchers. So kindly make your lecture simple and reachable, and please adhere to time. Now, may I request Devasis to start the session introducing Professor B.K. Mishra, our chairperson. Devasis, over to you.
Once again, I welcome all of you to this OCS extended lecture series, day 2. Past day was very great day. So we hope all of you will enjoy the day 2. Today's session 1 is chaired by Professor Vijay Kumar Mishra. I request Professor Vijay Kumar Mishra to chair the session. Before handing the mic over to him, I want to give a brief introduction of Professor Mishra. Dr. Vijay Kumar Mishra carried out both his PhD and DSc work under the guidance of Professor Dr. Gopabandhu Behera, Professor and Head of the Department of Chemistry, Sambalpur University. He retired as Professor of Chemistry in Sambalpur University. He has undergone internship at Dian Malito Wijongko, Indonesia, several market university, 2010, and this Arcana, Santiago University, Chile. Professor Mishra was member of the editorial board of the journal Natural Products, Bentham Publications. Professor Mishra has visited universities of South Florida, USA in 1990 and 2000, and University of Monsanto, USA in 2000. Professor Mishra has published 159 research papers both in India and foreign journals. He was the president of Orissa Chemical Society from 2015. I welcome you, sir. We have the honor that you present in this meeting. Thank you, and I request you to preside over the meeting. Professor Mishra.
Devasis.
Mr. Sir, Subhuni, ଆପଣ unmute करनांती.
Nice, unmute ଅଛନ୍ତି, but some technical problem is there. Professor Mishra, are you able to listen to us? No, shouldn't be.
Probably network problem. सर जब नेटवर्क प्रॉब्लम हो वीडियो ऑफ कर दियंतु कबा कोन वीडियो ऑफ कले टे नेट
Coach, sir, coach, he is no longer in the screen. So in the meantime, you unshare this technical session to slide. Devasis, please unshare this and ask Professor Vishwal,
Professor Nanda, sir.
Professor Nanda to put on his slides. Yes. ସାର୍ ଆପଣଙ୍କ ସେଠି ଶୁଭୁନି କିଛି ଆପଣଙ୍କର ଆଉ ଟିକେ ଥରେ ଟ୍ରାଏ କରନ୍ତୁ ନାଉ ୟୁ କ୍ୟାନ୍ ସି ଦି ସ୍କ୍ରିନ୍ ଅଫ୍ ଡକ୍ଟର ନନ୍ଦା ଇଜ୍ ଟୁ ଷ୍ଟାର୍ଟ ଦ ଲେକ୍ଚର ସୋ ଆପଣ ଟିକେ ବ୍ରିଫିଂ କରିଦେଲେ ସେ ଷ୍ଟାର୍ଟ କରିବେ ତାଙ୍କୁ ଟିକେ ଇଣ୍ଟ୍ରୋଡ୍ୟୁସ୍ କରିଦେଲେ ସେ ଷ୍ଟାର୍ଟ କରିବେ ଆଜ୍ଞା ଆଜ୍ଞା ଆଜ୍ଞା
प्रोफेसर सामल मैं अशोक मिश्र कहूँ से तांकर यदि ऑडियो प्रॉब्लम अछि से फोन रे कहि परबे फोन आपण फोन टाको अनम्यूट आपण एटा को स्पीकर मोड रखि दियंतु से फोन रे आपण कहबे आपण स्पीकर टाको खाली आपनकर ये माइक
ओके ओके लेट हिम कॉल से मते को
Thank you very much.
दर्शक
Some
ब्रेकिंग
mistakes. I'm not taking the.
I stopped my sound so
But two persons from Chile and
ताले मते
Indonesia.
कोंतु फोन रे कोंतु मु सुनेबी आपण केवल मते फोन करंतु और आई एम कॉलिंग यू सर
आपण इंट्रोड्यूस कर देतो वर्तमान
ना इट्स ऑल राइट आपण जाकर
आपण इंट्रोड्यूस
okay okay no problem Dr. Nanda
Yes, sir.
could you please introduce yourself sorry for this inconvenience just say a few words about yourself and yes
Yeah. Okay. Yeah. Good morning to all. I am Dr. Kamalakanta Nanda. I completed my Bachelor of Science and Master of Science degree in chemistry from Utkal University, Bhubaneswar, Orissa. Then I have done my PhD under Academy of Scientific and Innovative Research, New Delhi, on solar hydrogen generation. After completing my PhD, I got National Postdoctoral Fellowship and I joined Indian Institute of Science, Bangalore in Professor Sampath's group. And I worked there on electrochemical CO2 reductions. And after that, I obtained Got Energy Talent Fellowship from European Union, which is also awarded by the Marie Skoda Curie Fellowship. And I also obtained simultaneously another fellowship in Chile. It is the Department of Science and Technology of Chile. Then, therefore, I migrated from IISc Bangalore to Chile to work further on my research on electrochemical energy conversion.
okay
So today I will speak on chemical energy storage in small molecules.
okay.
It is
okay before you start the lecture what is the local time in Chile now
now it is 2 a.m.
oh god
or 2:10 a.m.
oh boy okay sorry to okay then it's better that you started fast please kindly go ahead till the chairperson joins kindly go ahead
Okay. Thank you, sir. I want to thank the organizers for giving me the opportunity and preparing this wonderful seminar. In fact, this pandemic has provided us an unique opportunity to bring all of us together from different parts of the world without emitting any CO2 by transportation through aeroplane or bus or train, anything, to the conference venue. And that is something really very nice. So as I have introduced myself, today I am going to talk about chemical energy storage in small molecule. But before coming to the presentation, I want to introduce something about Chile, something about my university, something about my city where I live. So our university is in the Chile, in the Santiago city, and this city is a kind of valley surrounded three sides by Andes Mountains, and our university lies in the heart of the city. It is Pontificia Universidad Católica de Chile, and it is one of the best university in the world, and it ranks around 121 in QS University ranking. And we have 5 campuses, and the chemistry department is located in the center of the campus also. And then coming to my research group, this is my research group. We work on the name of the research group is Laboratory of Coordination Chemistry and Electrocatalysis. We work on electrocatalysis, redox flow battery, nanocellulose, and spectroelectrochemical sensors. And he is Professor Maurice Isaacs, who leads the group, and he's Professor Tom Welton. He's from Imperial College London. He's our collaborator in nanocellulose projects, and I lead a small group of students, co-supervise them in electrocatalysis along with Professor Maurice Isaacs. So this is the content of my presentation. And as we know that the rigorous consumption of fossil fuels for energy, transportation, and chemicals is causing several environmental problems, particularly increasing in atmospheric CO2 level is causing greenhouse effect. And due to this greenhouse effect, the polar ice cap is melting. And you can see that this ice cap, burnt ice shelf, is melting due to greenhouse effect, and due to the melting of the polar ice cap, it cannot reflect back the solar radiation coming onto the Earth's surface, falling on the Earth's surface. Therefore, the global average temperature is rapidly increasing. Therefore, the time has come to depend on renewable energy resources, and particularly on wind energy and solar energy. And we have seen that the deployment of renewable energy, like wind energy and solar energy, are increasing, and the cost of the production is also decreasing. So at some point of time in the future, we'll have excess renewable energy, and we need to store those energy. The another point is that the solar energy or wind energy, they are not continuous. That means they are intermittent and diurnal, seasonal. So in any way, we produce more or less, we have to store this energy. So how can we store the energy? That can be stored in many ways. One is battery and supercapacitors. But when you see the battery and supercapacitor, they are in this side of the curve. That means either you need a very big battery or very big supercapacitor, and in scientific world, they are very low volumetric and gravimetric densities. But when we see to the chemical bond, that is the energy-rich compounds like hydrogen, they occur in the higher side of the curve. That means the chemical energy storage is the best way to store this renewable energy. And we know that hydrogen is a future fuel, and there are already hydrogen buses are running in Europe and in also South Korea. And we also know that this hydrogen has 3 times the energy capacity than it has in the gasoline. Also, the fuels can be produced by carbon dioxide reduction, or biodiesel we can talk about, and we can talk about also ethanol. We are using BS5 engines, and BS5 engine is nothing but ethanol plus petroleum. There is 5% ethanol, and now we are upgrading that. We'll change from petrol to ethanol to low carbon fuels. Therefore, the energy can be stored in energy-rich molecules, and we call it chemical energy storage. And there are many processes for chemical energy storage, such as solar thermal. Then we call one process artificial photosynthesis, electrochemical energy conversions. But I will talk about the last 2 processes. So artificial photosynthesis is a chemical process that mimics the natural process of photosynthesis, capture and convert sunlight, water, carbon dioxide into energy-rich molecules, storing energy in the chemical bonds. And we can see here that plant do the photosynthesis, they produce sugar and oxygen, and we can do the photosynthesis with the help of a photocatalyst in the lab, and we can find out that we can produce split water into hydrogen and oxygen. In fact, the first step of the photosynthesis is the splitting of water molecule. by manganese cube and complex. But the problem of this is they are all uphill processes. Therefore, at least we need a catalyst so that it can reduce the activation energy of the process, and also it can absorb sunlight for generation of the redox excitons, that is electron and holes, which will participate in redox reactions. Therefore, we choose semiconductor as a catalyst, or we can tell is a photoactive photocatalyst. And this process can be achieved in two ways: by suspending the photocatalytic in the solution and by irradiating sunlight above it. Here you will have a hydrogen oxygen mixture, and you have to do pressure swing adsorption technologies to separate those mixtures. And in another way, we can produce this split water just like electrolysis, but we'll use the solar energy here, and we can have hydrogen and oxygen and different electrodes, and in this way we can separate the hydrogen from the oxygen in this photoelectrochemical water splitting process. The other thing is that, as I have mentioned earlier, and as we know that the concentration of CO2 is increasing due to industrial emission and from the automobile exhaust, we can generally capture and convert this CO2 and build a carbon neutral society. So whatever CO2 we are producing, we can capture those CO2 and convert it to the fuels like formic acid and methanol. They are indirect fuels because they can be used in a fuel cell to generate electricity. Also, we can make ethanol, which can be used directly as fuel. We can make CO plus H2, which is a producer gas, and we can generate a lot of hydrocarbons. And also, we can generate other compounds like ethylene, which are industrially important compounds. So, but we have electrochemical energy conversion and artificial photosynthesis to store the renewable electricity in chemical bonds. Now, coming to the photocatalysis process, we have to understand the process. That is, what are the photophysical processes occurring on the surface of the semiconductor. So, when you see a semiconductor, when a light falls on the semiconductor, when its energy is greater than or equal to its band gap energy, we create charge carriers. Okay, these charge carriers are electron and holes, and this electron and holes has to be separated and transported to the surface of the photocatalyst to perform the redox reactions. But there are also the recombination of the photogenerated charge carrier in the bulk of the semiconductor during transportation, and also on the surface. If the surface is containing defects, there will be recombinations, or surface states, there will be recombination of charge carriers. And unfortunately, the recombination process is much faster compared to the charge separation and transport process, and in this way we lost 90% of the charge carriers. So to address this charge carrier recombination issue, one of the best process is to build a semiconductor heterojunctions. So what is a semiconductor heterojunction? When two semiconductors come in contact with each other having dissimilar band gaps. So there will be different band edges. Band edges means conduction band and valence band edge. And this, therefore, due to the different band edge, and when they come contact together, they will develop an internal electric field which will help in separation of photogenerated charge carriers. And due to band edge offsets, electron will go to one semiconductor, holes will come to other semiconductor, means one semiconductor will perform oxidation and other semiconductor will perform reduction. Hence, there will be low probability of charge carrier recombination. The other thing is to make a bulk heterojunction, because we know there are semiconductors. There are semiconductors which are active in the infrared or other regions, but due to their low band gap, there is a lot of recombinations, and some of them are not stable due to photocorrosion. But there are some organic polymers who have very high absorption coefficients, and they have very good hole transporting properties, but they have very low dielectric constants. Due to that, when the charge carrier is generated, they generate in a bound state, and we call them excitons. And they can only be separated when they can come contact with a semiconductor, nanocrystal, and polymer interface. And when we make this kind of interface, we call it bulk heterojunctions. And at this interface, we know that the semiconductor nanocrystal has a high electron affinity and high dielectric constant. Therefore, they can easily separate the electron from holes, and electron will go to the nanocrystal and hole will remain on the polymer phase. So in this way also we can reduce the charge carrier recombinations. So I tried both this approach and try to generalize which is better for developing a good photocatalyst for solar hydrogen generation. First, I constructed an all inorganic semiconductor heterostructure using cadmium sulfide and sodium niobate. I chose sodium niobate because it has a proper perovskite structure. It is stable at all the pH, and the octahedron, that perovskite is formula is AbO3 and it has a BO6 octahedron. Here we have niobium niobium NbO6 octahedron, and this octahedron is tilted due to higher size of the niobium. Therefore, we have an internal electric field, and this also helps in some separation of the charge carriers. But the problem of sodium niobate, it is active in the UV region of solar spectrum, and it constitutes 4% of the solar spectrum. So to make the absorption edge shifting to the visible region, we have made a heterojunction of sodium niobate and cadmium sulfide, and we have synthesized sodium niobate nanorods, and on it we have modified with cadmium sulfide nanoparticles. And from here you can see there is a dual band gap, one corresponding to sodium niobate and other corresponding to cadmium sulfide. And from this we can conclude that there is a heterojunction formed between cadmium sulfide and sodium niobate. Also, this formation of heterojunctions can be confirmed by transmission electron microscopy. First of all, we can see that the cadmium is coated on the niobium uniformly, forming a core cell kind of structure. And we have here a lattice match heterointerface. This is important because this lattice match heterointerface will facilitate the better transport of the charge carrier from one semiconductor to the another semiconductor. And we have explored the photoelectrochemistry of the semiconductor using a light from a solar simulator, and you can see that in the dark, the faded lines, you will find there is no current in the dark. But there is very little current in the dark. But upon illumination, the current drastically increases. And if you see this red line and this green line, this is the photocurrent curve of sodium niobate nanorod, and this is the photocurrent curve of cadmium sulfide sodium niobate nanorod. There is a drastic enhancement in the photocurrent upon the modification of cadmium sulfide onto the sodium niobate nanorods, and it is also reflected in external quantum efficiency, that is incident photon to current conversion efficiency. And you can see that there is around 20% conversion efficiency in the visible region of the solar spectrum, which was earlier absent in the sodium niobate nanorods. Further, we have employed this catalyst for solar hydrogen generation, and we illuminated from a solar simulator, and we can see that there is around 6 times increase in the hydrogen productions compared to the cadmium sulfide. And also sodium niobate don't give any hydrogen because it is UV active, and solar simulator contains very little UV radiation, so we do not get any hydrogen in case of sodium niobate. So there is a drastic enhancement in solar hydrogen generation by cadmium sulfide sodium niobate heterostructure catalyst. And one thing we can see that as a cadmium sulfide is a low band gap semiconductor, and its decomposition level is in between the band gap, therefore it goes photocorrosion. And therefore after 4 hours you see the rate of hydrogen generation becomes stable, and after 6 hours it decreases. And we confirm from the ICP, that is inductive coupled plasma spectroscopy, that cadmium sulfide is breaking. That means cadmium ion could be identified in the solution. That means the semiconductor is decomposing. But upon the formation of cadmium sulfide sodium niobate nanorod heterostructure, we did not see any photocorrosion, and we have a steady increase of the hydrogen production with time. So the photocorrosion of the band gap semiconductor, low band gap semiconductor, can be suppressed by forming the heterojunction. We have studied the charge carrier dynamics by time result photoluminescence spectroscopy, and we have obtained that there is an enhancement in the carrier lifetime upon the formation of heterostructure. And therefore, due to formation of heterostructure, we have a lattice match heterointerface, we have a better stability, and also we have better separation of charge carriers, which combinedly contribute to higher solar hydrogen production rate. Then we construct a P3ST CDS bulk heterojunction photocatalyst. We developed cadmium sulfide thin film by chemical bath deposition, and I here used organic complexing agents because earlier literature they use ammonia as a complexing agent, and ammonia is very volatile. So during the chemical bar deposition process, even if you make some tight or something, it leaves the solution. So there is a change of pH. So your thin film are not uniform, and they have they are not continuous. But when I use organic bases like ethanolamine, I got a morphology of the cadmium sulfide thin film, like microstructure of the leaf, and this microstructure of the leaf helps the leaf to absorb more solar radiation than a flat surface by total internal reflection. And when we examine this cadmium sulfide thin film with transmission electron microscope, we saw that each flake consists of very tiny nanoparticles, and it can also be observed from the SAT pattern. And from here also we can see that we have hexagonal cadmium sulfide. Also, it has been confirmed by XRD, and the finding of the amorphous region and the crystalline region in the TM of cadmium sulfide P3ST CDS, we can conclude that we have formed a heterointerface between P3ST and CDS. To further characterize the heterojunction and to optimize the concentration of poly 3-hexyl thiophene, we have performed Raman spectroscopy. So we know that if we have a C-C double bond and we put a strain on it, the Raman intensity will increase. It has been seen in case of carbon nanotubes. We performed on the same analogy, we performed the Raman spectroscopy, and we found that at 0.28% P3ST CDS concentration, we have higher strain on the double bond. That means we have highest number of P3ST and CDS interface when we modify the cadmium sulfide surface with 0.28% P3ST CDS. And also from the photomerism spectra, we could see that there is a minimum charge carrier recombinations, radiative charge carrier recombination in case of 0.28% P3ST CDS heterostructure photocatalyst or thin film. So we choose this as our optimal concentration, and we further proceed to characterize it by diffusion reflectance spectroscopy, and we can see that upon modification of P3ST to the cadmium sulfide, we could shift the absorption edge to the visible region of the solar spectrum, to the red region of the solar spectrum. Also, in the UV visible absorption spectra, we could see the inter-band gap transitions, which also confirms the formation of heterostructure. We have also done the electron energy loss spectroscopy to confirm the heterostructure formation, and also the XPS, which is not shown here due to time constraint. And we compare the photocatalytic hydrogen generation of cadmium sulfide, sodium niobate nanorods with P3ST cadmium sulfide thin films. And we could obtain, we could see that although we have a better IPCE, little better IPCE in the red region of solar spectrum, but the overall IPCE of this polymer semiconductor heterojunction is less compared to the all inorganic semiconductor heterojunction. Although we increase the solar hydrogen generation rate compared to the cadmium sulfide, but we could not achieve the expected rate as we achieved in cadmium sulfide sodium niobate nanorod with this P3ST CDS heterostructure photocatalyst. And it is due to the high rate of radiative recombination that is already present in the P3ST. It is a fluorescent molecule also, and due to this thing, we are not able to separate the required amount of charge carriers, which will give you better better solar hydrogen generation. And also it has been confirmed by time resort photoluminescence spectroscopy. So from this, we concluded that all inorganic heterostructure photocatalyst or photoelectrodes shows higher solar hydrogen evolution rate in comparison with the bulk heterojunction or dye-sensitized photocatalyst, owing to higher carrier density, better charge separation, and due to smooth heterointerface and high dielectric constants. And with this, I will come to the other part of my talk, that is electrochemical energy conversion, that is electrochemical CO2 reductions. And this was discovered by Hori in 1986, that copper can electrochemically reduce carbon dioxide to hydrocarbons and also to some oxygenates like formates. And after that, there are a lot of research in this field, and it has been found that copper is the only metal or only electrocatalyst which can produce 16 different hydrocarbons from CO2 reduction. Other metals, some produce formates, some produce CO, and and all the varieties of products and high Faradic efficiency of the hydrocarbon products can be obtained only with copper. It is because
2
it
minutes.
is due to the intermediate binding energy of the copper.
Dr. Nanda, you have 2 minutes more.
Only, okay. So we can see that in the electrochemical CO2 reduction, the surface plays a very important role, and we can see that this copper 111 surface gives methane, copper 110 surface gives ethylene, and copper 110 surface gives oxygenate, and 100 surface gives us ethylene. And therefore, we have to study the electrolyte interface to know about this CO2 reduction process and to design a electrocatalyst. And in our lab, we have designed various electrocatalysts by engineering the copper surface so that we can selectively produce oxygenates. Also, we can selectively produce hydrocarbons. And you can see the range of copper catalyst. What I will discuss here about copper 1 and copper 2. And copper 1, we see that it is 110 oriented, and copper 1 is 111 oriented. Therefore, we have a different selectivity. And we have done these selectivity studies with constant potential electrolysis and with also differential electrochemical mass spectrometry, which is a technique which determines the transient products during the electrolysis, even if they are in the very low concentration. And we have obtained that on the copper 1 surface, we get only methane as a product in constant potential electrolysis, but here in the DEMS we get some amount of methanol, but when we increase the potential, the methanol concentration is decreased and methane concentration is increased. It is because on higher potential we have a thermodynamic higher applied negative potential, we have a thermodynamic product, and at the lower applied potential, kinetic products predominant. Also, we found out that we have some methane in the low potential on 110 surface, and on 110 surface, on going to higher potential only we get ethylene. That means on 110 surface, we have a different mechanism for methane and ethylene formation, and this is under further investigation. And the last, I will introduce the pair electrolysis process, where we have seen that present electrolyzer, on one side we have a water oxidation, other side is hydrogen production or CO2 reduction, and this oxygen evolution process, it has very high overpotential, and due to high overpotential, this process increases the overall cell voltage and input cost of the electrolyzers. But if we pair with alternate oxidation reactions, which have higher economic value than oxygen evolution reactions, we can produce those hydrocarbons, and also at the anode some value-added products, that is platform molecules. Therefore, we can increase the value of the electrolysis and also the input voltage of the electrolyzers. And these are some examples of the
Dr. Nanda, please conclude.
process.
Dr. Nanda, please conclude.
In conclusion, we can say that the carbon-based liquid fuels are ideal for long-term energy storage because of their high energy density, and charge carrier separation is more important while designing a heterostructural catalyst than the light harvestings, and we can suppress the photocorrosion of narrowband gap semiconductor by forming the heterojunction. And also we have to study the electrochemical CO2 reduction at the molecular level and study the processes occurring at the electrode-electrolyte interface, so that we can design a better catalyst for CO2 reduction, which will produce selectively one product at the electrode and also require very low over potential. And also we have to design the pair electrolysis process to decrease the overall power consumption of the electrolyzer, and also to find a value-added product at the anode, and exclude the high over potential requirement of oxygen evolution reactions. With this, I thank you all. And at the last, I want to say that if we want to make the world more sustainable, then we need to find a solution for carbon dioxide. Thank you.
Am I audible now?
Yes, sir. Yes, sir.
Am I audible? One or two questions for Dr. Nanda. Audience. later on, those who have some questions, they can write it in the chat so that you can see it and you can ask them.
Yes.
And as there are no question, we can thank Dr. Nanda. But how to maintain the pH? They are changing the pH.
See, first we use a buffer.
The pH during
Use a buffer, bicarbonate buffer, because
hydrogenation pH
this carbon dioxide,
buffer.
the
Okay.
solubility is very low.
Buffer.
So you have to use a
Right.
buffer to increase the solubility. Still, it is low, but it is more than the your other electrolytes. You could use ionic liquid to enhance the
Okay.
solubility of carbon dioxide, but ionic liquid is very difficult to handle. So use a bicarbonate buffer.
Right. Right. Now, organic buffer. Organic buffer is better, I think.
Organic water buffer will
Okay.
not conduct.
Thank you.
Will not
Very much,
conduct the electrolysis process properly. There will be also a problem. We need higher over potential in organic buffers. So bicarbonate buffer is the best solution.
Okay.
Can I have
Okay. Thank you. Thank you very much.
Sir, can
Yeah.
I have a question, please? Just one.
Yes. Yes.
I have a question
Yeah.
regarding
Yeah.
first part where you showed hydrogen production.
Yes,
So
sir.
the production of hydrogen that you showed in the graph is in micromolar quantity
Yes.
per hour. And the
Yes.
second part of the question is that you studied corrosion until photocorrosion for until just 8 hours. But we expect the catalyst to be used endlessly. For these are expensive materials and they should be used for a long time and produce good amount of hydrogen.
Yes, we have done that because we have a pilot scale project. Even we have done in a 1 liter reactor for more than 24 hours. The cadmium sulfide, sodium niobate nanorod performed a better photocatalyst among whatever catalyst we have designed, and there is only 20% reduction in the hydrogen production rate after 24 hours. That was highest we have done. We could not do it for longer time.
Okay. So keep trying, but it has to be cost effective. The amount
Okay.
we good enough.
Therefore,
But up to 8 hours is okay, then it will continue, I think. Up to 8 hours, if it is okay, then it may continue. Okay. So thank you very much. Other speakers are ready. Who is ready now?
Professor Misra, I think you are using two systems. There is an echo
Yeah.
sound system. So if you are using two, if you are logged into this with the two systems, there will be echo.
I'm using only one.
Okay,
Okay, who is the next speaker present?
Professor Aditya Narayan Panda.
Vijay sir, namaskar.
He
Next
is
speaker,
there now.
Professor Aditya Narayan Panda. He is here.
lecture 2.
Okay. So welcome, Dr. Panda.
Thank you,
Welcome,
sir.
Dr. Panda.
Thank you.
And for the audience, let me introduce Dr. Panda. He is, professor, the youngest professor, I think. He is a professor in Guwahati. He is basically dealing with Professor Murthy in Dhenkanal. And he is promoted after joining Guwahati in 2007. He promoted to professorship.
Hello. I could not hear you, sir, properly, but I'll start now.
Yes, sir.
Yes. So I'll share the screen first. Yes. So I hope my slide is visible.
Yes. Go ahead.
Yes, sir, visible,
Yes.
sir. Yes, sir.
Yes. So yeah, so thank you, Professor Mohanty and Professor Mahapatra. Thank you very much for your kind invitation. It just feels fantastic to be here. I am actually attending this set of seminar from Odisha Chemical Society for the first time. I mean, online one. So this just feels fantastic. Other distinguished attendees, Professor Samuel. Of course, I'm sure that sir would not remember me from my 5 years of Revensa. It's been long. Professor Mishra sir, we have been in touch on and off. And I also saw in the morning when the meeting started, and I was not able to properly join into this. I could see, Anadi sir. Thank you very much, sir. It's nothing much to say. I really love, Professor Anadi sir. So thank you for everything. And let me start. So, as the title says, we are going to look at a little bit about the biomolecular chemical reaction, and my talk is going to be a little bit different than what we have seen over the last 1.5 days. It's going to be computational and theoretical studies. Let me start with this slide, which sort of summarizes our recent works, and most of the work that is presented here, this was done by one of our, Odia students who is actually now doing a postdoc in US. We have been, designing polymers, small molecules for organic LED applications or photovoltaic applications in recent times, and we have been looking at also helical polymers, their properties, in particular the excited state properties, and the small molecules also, excited state dynamics of small molecules, like at the bottom we can see the blue, this one is a small molecule excited dynamics, what happens when the molecule goes to the excited state. In addition, we have also been looking at this part here, which is the one that I'm going to talk about today, which falls under a category of studies what is called reaction dynamics. So let me first acknowledge the people who have been involved in this. Devas's work, a part of his work I'm going to present today. In addition, the collaborators have been Javier Oez from Spain and Stuart Althrow from UK, and in recent times we have also we are also having Tomas from Madrid, Spain. So these works were done in collaboration. Part of the work we did here, and then part of the work was done in Spain and the UK. So this is the outline of my talk. I'm going to give you a brief of what is exactly that I'm going to talk about, and then it is going to be the methodologies that we have used, and then few examples, and then trying to understand what exactly, how exactly the reactions are happening. So, as I said, since I'm going to talk about this topic, what is called reaction dynamics, I mean, let me just tell you in the beginning itself, this slightly falls, in the area what is called chemical physics, right? So we use methodologies from quantum mechanics or classical mechanics, and then solve the dynamical equations of motion to study the reaction. So as a chemist, when we talk about chemical reactions, we look at this sort of a picture that is shown here, taken from Wiki. Whether it is a synthesis or a decomposition or a single or a double replacement reaction, we always talk about a transition state. So we have reactants in the left hand side here, we have products on the right hand side here, and we have the transition state here. And that is how we are used to look at the chemical reaction. And of course, we know that there is something called an activation energy, and then in presence of a catalyst, the activation energy becomes smaller, and then the reaction proceeds. That is how we know that the transition state as it is. This is one of the measurements that was carried out in 2015, appeared in Science. By Baraban et al., which actually measured the energy of the transition state with their vibrational energies, everything. Like, this is the first time everything was clearly measured, right? So this is a perfect example of acetylene isomerization, where for the first time they showed that everything can be done, that characterization of the transition state. So coming back, so we actually in chemistry we know about either an exothermic reaction or endothermic reaction. The energy is released or the energy is absorbed. So that's how we look at reactions. So this is the exothermic one on the left, and the right hand side we have this endothermic process. So two things are important for us here. The first one is the activation energy. We always look at like how high the wall is, the barrier is, right? So how much energy we need to push it over the barrier, right? So in addition to having this kinetic energy part, we also have something called the orientation of reactants during their approach. So as you can see in this picture, we have three situations. In the first one, there is no reaction because the kinetic energy is insufficient. There is not enough energy to push the reaction over the barrier, right? To push the reactants over the barrier. The bottom one, the reactants are incorrectly oriented. So reaction doesn't happen. So the middle one says it has to have optimal energy. I mean, the applied kinetic energy has to be optimal, and then the reactants have to be properly oriented. And that is when the reaction is happening. That is in the middle row of this slide. So the questions that we ask ourselves in our lab while doing all these calculations, we ask these questions, very simple questions. How does the kinetic energy affect the reaction processes? So we have this kinetic energy starting from, let's say, 0.1 electron volt to 10 electron volt. So how the reaction gets affected to this range of kinetic energies? And we have to remember that the reactants themselves, they also have their internal energies. When we talk about internal energies, this means the rho vibrational energies. So that is inherent, right? We know that 0 point energy is not zero, so there is some inherent energy that is already there in the reactants. So when we talk about the effect, or the idea that we want to know what is the effect of kinetic energy, we actually talk about kinetic energy and the internal energies which are already there. And we would also like to know what about the product channels. So there could be many products. So are all the product channels available, or there is a dependence on the kinetic energy also, right? What about the approach angle effect, orientation effect? Reactants are approaching like we saw in the previous slide. So if they approach like in a collinear fashion, if they approach like in 90 degrees, if they approach in 20 degrees, whether the approach angle also has an effect on this. And once the products are formed, what about the rho vibrational energies of the products? Whether the products are formed in the ground rho vibrational state, excited rho vibrational states, or the question that exactly we ask is, what is the rho vibrational distribution? And that's what we ask. So like I said, the language that we use is what is called the reaction dynamics, or exactly calling it like collision studies or scattering studies. And we actually can look at
What other conversation?
Aditya Panda sir, କିଛି ଶୁଭୁନି? You are not audible.
Make a call. Mute and unmute.
Unmute ଅଛି ତ sir. Unmute.
Mute and unmute. Reset. Call କରିକି କୁହ to mute and unmute.
Or restart the computer. Aditya Panda sir.
Restart କରିବା ଦରକାର ନାହିଁ, ଖାଲି mute unmute କଲେ ଆସିବ। Is coming back, yes. You have to click the link that was provided to you. कॉल करके कह लिंक टाक क्लिक कले हम
problem.
দেবাশিস এটা অনাদি সারঙ্গ স্ক্রিন রে দেখাও
हां सर आपन स्क्रीन देखा जाउनी
हेलो
এটা দেখাইবে এসপি দা স্ক্রিন মানে সার ওই অনশেয়ার মানে সারঙ্গ অনশেয়ার কর এই যে অনাদি সারঙ্গ
आउट
अन्नदी सर
এই দেখাও ইউ আর ভিউইং এসপি দা স্ক্রিন দেখাও জি
ये स्क्रीन टा
कहाँ स्क्रीन
এই স্ক্রিনটা এসপি দা সারঙ্গ র উপর লেখা ইউ আর ভিউইং এসপি দা স্ক্রিন তুমি মানে
ये कौन केंदी तो गेस्ट अछंती
You have to unshare so that I can share it again.
सीधा सर आपण शेयर स्क्रीन टा टी बंद कर दियंतो आपण तो टू को
No, I can. My sharing is off.
Yeah.
Your sharing is on. Somebody is sharing, so I.
দেবাশিস
सर सीधा सर क्या है इसमें देखो
দেবাশিস তো হোস্ট আছে এসপি দা সার আগে টেম্পোরারি রিমুভ করে দে তারপরে হই যাবো
अच्छा अच्छा
Hello.
Now
होंडा से ट्राई करो
हां एबे नाउ पंडा सर ट्राई करो
Yeah.
रिमूव कर दो
Is it visible now, Dr. Mohanty?
yes sir visible
You have to give me 5 more minutes than record. I don't know for how many minutes I was not audible. So I'll try to go quickly from now onwards, but some relaxation is required.
yes
Okay.
Okay.
So I will restart with this slide. Yes, sir.
You can make more.
Yeah. So I'll start with this slide, which tells us that the right hand picture tells us the sidewise scattering. When the scattering happens, whether the products are scattered in the backward direction or in the forward direction or in the sidewise direction. In addition, we also have what is called a near side or a far side scattering. If the scattering, if the approach happens in the upper hemisphere, we can think of a globe. If it happens in the upper hemisphere, the scattering, then we call it a near side scattering, or if the result or the scattering happens, the products are scattered into the lower hemisphere, we call it a far side scattering. So we are going to look at all of that. So I'm going to talk about a reaction of this type, reacting with BC giving rise to AB plus C, single replacement reaction. And then these 3 reactions I'll quickly go through, which we have been working on for some time. One is this Br plus H2, which is endothermic, which is an endothermic process. And then the second one is H minus H2 giving rise to H2 plus H minus, which is a thermoneutral. And then we have the third one, which is an exothermic reaction. All right. So as you see on the right hand side here, starting from there are 3 situations that I have shown here. The red lines are for the reactants and the black lines are for the products. So from the reactants, you can see you can go to the product like that, right? So that's what we know, going through a transition step. And at the bottom, we see a slightly different picture where we have an exothermic reaction, but the path is slightly different. It goes like that. At the top also, this endothermic reaction also, there is a possibility, we'll see now, that the reaction can happen like that. All right. So these are the situations, and of course in the middle we have the thermoneutral process. So like I said, the simple reactions are not so simple. We show here what is called a direct reaction. A approaching BC, the BC bond length increases. So the reactions are about bond breaking and bond forming. So the BC bond is increasing, the BC bond breaks, and the AB bond starts forming, right? So that's the reaction. So we call this a direct reaction. So A approaches BC, the BC bond breaks and AB form. That's the direct. But we can always talk about an indirect or what is called a time delayed process, where again A approaches BC, BC bond length increases, but at a certain point of time, all the three stay together, like at the top of the transition state, or like I showed in one of the previous slides, somewhere in a well, okay, there is a minimum. So these three can stay together before breaking into the products. So we call this an indirect process or indirect mechanism for the reaction. So typically these are the signatures of direct or indirect processes. So we look at the direct process on the left hand side here, which are typically backward scattered, and then we have here a typical process which is indirect process or a time delayed process, where the scattering happens all along the angles, like all the angles, right? Products get scattered everywhere. Or in addition, we can have a slightly different one which can have both of them, a mixture of both direct and indirect, which is shown at the bottom. All right. So coming back to the questions again. So the question is, how difficult is the challenge, and what about the time consumption, and what about the time versus accuracy? It's like how accurate you want the results, and how much time it is going to take. So we basically solve the Newton's equations of motion, F is equal to ma, or Schrodinger's equations, either the time dependent Schrodinger's equation or the time independent Schrodinger's equation, to get the observables and to understand the mechanisms. So here is a typical picture that we come across. So like we know, we have to first define the Hamiltonian operator for the system, and the Hamiltonian is its own. I'm not going to discuss too much of that. So we'll go forward to the results. All right. So here is the potential energy surface for the BR plus H2 system. Okay. All right. So the Hamiltonian that we use, Hamiltonian operator, it has two parts: the kinetic energy and the potential energy part. Kinetic energy is, of course, you have to write it down. Potential energy part, which gives us the idea like where and how the reaction could happen. Like that's what it gives, and that is something that is shown here for BR plus H2 system. This is a collinear approach that we show here. On the left hand side, as you can see, this is the reactant part and this is the product part here. So this is an endothermic reaction. It goes via this barrier, this transition state here. All right. On the right hand side, we show the various reactant row vibrational states and the product row vibrational states. Like it clearly tells us how much kinetic energy minimum will be required to climb the hill. For example, here this is the hill. If you start from here, if you start from V is equal to 0, so this much energy will be required. If you start from V is equal to 1, you are already sort of at the barrier, sort of, right? This picture here at the bottom tells us about the angle of attack. It says that if the reactants approach at 0 degree angle, the reaction is very much feasible, and as the approach angle increases, it approaches towards 90 degree, the barrier becomes too high, so that the potential becomes too high, so reaction is slightly difficult. So here we show a slightly different picture. of of Br plus Hd, where instead of H2 we have changed one of the hydrogen atoms to D. So this is called the mass effect, the kinematic effect, and as you can see, the potential surfaces are different for this Br plus Hd giving rise to BRH, and Br plus Hd giving rise to BRD. So these are two different systems. In that sense, basically two different products are possible, and then that is of course visible. So the right one, this one is the BRH product here, this is the BRD product here. You can see this angle is much smaller here, indicating that there is a quantum tunneling that could happen. So here some of the results we have. These are what is called the probabilities, something that we have already said. Sorry. So probabilities, as we can see, this BRH product is in the black line, BRD is in the red line here. The situations are very different. So we have two different products. The probabilities are totally different, right? You see, there is so much of these oscillations here in the probability curves in case of this red line, right, in the BRD. The other observable that we have is what is called the integral cross section, and you can see again, like in the previous slide, we have total differences between these two paths, these two products, right? The BRH is here, and then the BRD there. So here is the rotational distribution. That is something I talked about in the beginning. It says that at a particular collision energy, kinetic energy, how the product rotational distributions are going to look like. So in case of BRD, in case of BRH. So these are different. These are very different from each other, which is of course understandable. And here we have the most important result that we have, what is called the differential cross section, which tells us the products, how they are going to get scattered at different energies. So here we have the BRH product, here we have the BRD product. They're different. They're very different at different energies. So for example, at 1.5 electron volt, we have this line here for the BRH product, and then that particular line is sort of skewed in the case of BRD product. We can go from the energy dependence to the so-called the time dependence. We can do a Fourier transformation, go from this differential cross section, which is shown here at the top in the angle and energy coordinates. You can Fourier transform it, go to the angle and the time domain. Angle and the time domain. This is the x-axis, here is time. So you can do that, which clearly tells us that if there is a time delayed mechanism at all. So on the left hand side, you can see all of them appear around the same time. On the right hand side, on the other hand, we have there is something that appears little bit after the first set of lobes appear. All right, so which tells us that could be a time delayed mechanism. So we'll just go to the next topic. I have just skipped 3 slides. If you need some more information, we can of course look at it later. So we have the second topic that I said is H minus HD. So this one is H minus H2 is thermoneutral, and then if you put a D there, it is going to affect the kinetic energy part, right? The potential is going to remain the same. So it is a thermoneutral process, like we saw in case of Br plus HD. So here also there are 2 products possible, H2 versus HD, and then we have again different probabilities for different products. And then we can look at again the energy and time dependent differential cross sections. So we have energy differential cross section versus time and the angle. Here again for differential cross section for energy and angle for so at the bottom again we have the Fourier transformed picture, which tells us the DCS as a function of time and angle. You can see that the time part, there is only one lobe in both the cases, which means that there is only one type of mechanism that is taking part. In this particular slide, on the other hand, we see that there are two different lobes, as you can see here, and at the bottom, as a function of time, there is one here and there is one here. That is better shown in the next slide. As you can see, this is in energy, this is in time, and then you can actually see that you can clearly differentiate between the two different types of mechanisms, like we have done at the bottom here. We have just separated these two parts from each other, and then we could clearly see that there is a clear effect of time delayed mechanism on the reaction that is here, and the backward reaction mechanism that is there. All right, this is a straightforward, and this is the time delayed mechanism that is shown here. And a two-dimensional picture is of course shown at the bottom, clearly telling us that the reactions, there is an effect of time delayed process also. So this is the third reaction that I thought of quickly showing you. This is an exothermic process, like I mentioned in the beginning. The energy level diagram is shown here, and then as you can see, the reactants are here, the products are here, and the reaction goes via this OL. Okay, goes via this OL. So there is a possibility that all the three atoms can be clubbed together, can stay together for some time. You can measure their lifetime, of course, and then before they dissociate into the products. All right. So again, these are the different results that we have. The time dependent quantum mechanics, time independent quantum mechanics, classical studies, all the results, they match very well with each other, and we calculated the cross sections, which clearly says how the reaction cross section should look like for a typical exothermic reaction. It starts at this much high, and then it goes down. And then there is this reaction rate constant, of course, we calculated compared with the experimental result here. As you can see, there is a sort of a good comparison between ours and the experiment. So to show you the the results, any information that we can get from the classical results here, what is called the deflection function is shown. As you can see at the bottom, the deflection function is plotted as a function of scattering angle and the total angular momentum. And as you can see, there is a clear-cut mechanism differentiation that we can have. So this is one mechanism that is happening here. There is another one there. Similarly, at another collision energy, this is there. There is another lobe there. On the right-hand side, we plot the lifetimes of the trajectories for scattering angle and capital J, the total angular momentum, and we can see that at lower collision energy, there is a possibility of indirect mechanism happening. And we can look at two of the trajectories. This is a typical direct trajectory that we have. As you can see, the A atom being heavy, neon atom, it is moving slowly, and then the BC is coming towards A. Then the C gets transferred directly, and then B goes back, and then AB is formed. So this is what is called a typical direct process. And then we can go back to the next slide to look at this particular movie here, where it is going to be slightly different, what is called a complex forming or indirect path. As you can see, BC is again approaching towards NE is moving slowly. So, and then all three of them would be close to each other for some time. As you can see, the C, the smaller one, the hydrogen one, is actually trying to roam around, right? So all of them stay there for some time before the B goes out, and then the products are formed. So I stop here to while concluding that everything, these bimolecular processes can be studied using quantum mechanics or classical mechanics. And then we have shown that there is a mixture of both the reaction mechanisms happening. And if anybody of you are interested to know more about it, please ask, or you can send me an email, or get the number from Mohanty sir or Mohapatra sir, and then just WhatsApp me, and then I will try to answer all your questions. That's all. Thank you, Dr. Mohapatra and Dr. Mohanty.
So thank you very much. Nice talk, but there are disturbance during the talk.
Yeah,
So,
that is probably not avoidable.
Yeah, Panda is very except anybody can ask him to also. You can contact him. Very good. He can tell you. So thank you very much, Professor Panda.
Thank you again. Thank you.
Yes, I think Dr. Vishwal is here, so you can start sharing. Yeah, Dr. Vishwal, you can start sharing your slides.
Okay.
Then the chairman will, session chair will.
So is it visible now?
Yes, absolutely.
Okay, thank you.
Please wait for chairman. Professor Mishra is there. He's chairing the session, so maybe he will be trying to connect you. Sir, are you able to listen to us, Professor Mishra? Okay, then I think with permission of the chairman, I would kindly request Dr. Vishwal to introduce you.
Yeah, you can accept our panel also. You can try. Yeah, because 10% is next speaker is.
Yeah,
You know,
the next speaker is ready.
Dr. Vishwal, he is nice. Vishwal, Dr. Vishwal. Yeah.
I mean, sir, आपन कथा बहुत कटि जाउछि किछि सुबु नै. Maybe Dr. Vishwal
not audible.
Audible.
Hello, I can. Yeah. So maybe I'll start. Hello.
Okay.
Dr. Vishwal, you introduce yourself and continue.
Yes.
The audio problem.
So I'm Vishnu Prasad Biswal. So I did my bachelor, like BSc from Dhenkanal Autonomous College. Yeah, and then master from Utkal University, Department of Chemistry, and then I have done my PhD from National Chemical Laboratory, Pune. I did two postdoc from Germany. So the first with the help of Alexander von Humboldt Foundation. And my area of research is basically porous material for different applications, particularly molecular separation and of course solar fuel production. And with this brief introduction, I would like to thank OCS and the organizers. Actually, there is some background noise.
Go ahead, we shall see.
Yeah. So
I am muting all. Sir, you unmute yourself and then tell. I am muting all. Okay. You will be also muted.
Okay. Very good publication. Very good point. Very high.
Now unmute yourself. Professor Mishra and Vishnu sir, you can unmute yourself. I mute all. Yeah.
So is it okay?
Yeah, it is okay.
Okay, thank you. Yeah. So I would like to show my thankfulness to the OCS and the organizers for giving me this opportunity, because unfortunately last time I was unable to, like I couldn't manage to attend OCS meeting in the December. But this time I'm fortunate to make it. And today I'll be talking on porous materials, particularly two porous material I will introduce. And I will talk their application towards molecular separation and solar fuel production if time permits. So let me straightforward go to air pollution, because we all know what is air pollution. So it doesn't need extensive introduction. So air pollution has been the major global concern, as we all know. And hello, is it okay? Hello.
Yes, sir. Yes, sir. Continue, sir.
Okay, thank you. Yeah. So basically, air pollution, as per WHO, it is turned as a slow poison, because 7 million deaths around the world every year is happening because of air pollution, and unfortunately 2 million deaths are due in India. So if you consider the components, the major chemicals that cause air pollution is oxides of carbon, sulfur, nitrogen, and some other gases like methane, ammonia, etc. So if we talk about how the contributions towards air pollution, if we see transport, industry, and waste burning is contributing about 75% of air pollution. As a result, what is happening, the global temperature is increasing. As we know, what is global warming. So glaciers are melting because of the rise in temperature. Methanes are coming out to the surface of the earth. So as a consequence, what is happening, the ozone layer is depleting. So how we are going to approach all these major issues? So as a general people, what we can do reforestation. We can use more and more renewable energy, and of course we need to restructure our infrastructure, industrial infrastructure particularly, and recycle our products as much as possible. However, as a scientist, what we can do, we can store the gases, we can do gas separation, we can use those gases to convert them into value-added chemicals. So I'll talk mostly on this aspect today. So coming to gas separation basically a technique which has been used to split different gases. Like one component of gas can be separated from a mixture. So it has two major applications. The first one is in coal fire plants, and second one is purification of natural gas. If you talk about what are the major technologies already been developed, that the two comes like adsorption and cryogenic distillation. I'll not go into detail. If anybody has questions, then of course we can discuss that. The major thing I want to highlight is it consumes high energy, and both the processes are costly and inefficient. So question here arises, is there any alternative or convenient option? My answer would be yes. So there is some other alternatives are available. I would say say membrane. So membranes are in general, it is a thin barrier which allows selectively some component of the gas to pass through membrane pores, and some are they retain. This is particularly interesting because of its modular nature. We can couple with many processes. The costs are low, or the operating costs are low, and it is importantly it is clean and green process, because it only the separation is based on physical and chemicals are not involved. So if we talk about the mechanism, how this molecule or gas transport occurs, there are through membranes. Basically, there are three kind of mechanism. The first one is called Knudsen diffusion, where the pores are very big, so that only the smaller all the molecules will pass through, but smaller molecule will pass through faster, and the bigger molecules follow. However, in the molecular sieving process, the pores are exactly pores are favorable to allow only the smaller molecules, and bigger molecules they reject. So this is called the molecular sieving mechanism. And in solution diffusion mechanism, what happens? The gas molecules first they get solubilized inside the membrane and they dissolve. If we talk what are the materials people have been using for do this gas separation, the first material is about 95% of gas separation market is dominated by polymer membranes, which is of course simple to process and low cost and easy scalable. We can scale up polymers very easily. And the limitations are the selectivity permeability trade-off, low thermal and chemical stability, and of course, as a result, the operating time is short for polymeric membrane. So another material also people have been using, that is called zeolites. So they have advantages like the separation. They have rigid and defined pores, so that the molecular sieving mechanism comes into play here, and one component can pass through and the bigger molecules they cannot pass through. So this is good material used in heavily in industrial purpose. Of course, it has limitations like inorganic nature, so you cannot tune the structure, and the synthesis is also difficult. So our like question is here, like if we can combine both the advantages, so whether we can get a material, or is there any existing material that can be useful for gas separation. So I'll straightforwardly come to a material class that is called metal organic framer. From the name itself, you can see there is two component. One is metal component and another one is the organic component. So when the metal and organic linker, like bidentate or polydentate linker, they coordinate, they form beautiful crystals. And this kind of, we can see these are some crystals, and you can see the connectivity, like this is the linker and this is the metal cluster. So they form a three-dimensional structure, so that inside they have some pores. I'll come to that a little later. And so far as synthesis is concerned, there are several ways we can synthesize them. And also I would tell, like these materials are so useful nowadays, and these are emerging materials, so people have started synthesizing them in tons. So you can see this is the BASF Germany. They are producing this kind of porous materials in tons. You can see how they are producing here. So far as the property is concerned, like these materials are highly porous. I would give one example, like suppose if you take this material like 1 gram, so it will be 1 rupees coin. So it will take only 1 rupees coin, the space of 1 rupees coin. So the surface area inside this material would be close to like 8,000 meter square per gram of material, which is equivalent to a small football field. So I can better explain you, like if you take one cylinder, and the pressure would be like 3,600 psi. So if you put this 1 kg of this material and your pressure reduced to 4 times, so in that way, in one cylinder we can store up to 4 times more gases. So how powerful this is, this more porous materials are. So I will show you a video to just to give you a brief like idea how they look like in the inside the crystal. So you can, from this video, you can see there are a lot of crystals, and from, if you zoom only one crystal, you can see the how the network look like. So gases are basically come in and they get trapped inside. So like here you can see this is animated video. So gases come in that they trap inside, and whenever we require, due to pressure difference, we can basically recover them. Okay, so there are enormous of opportunity to tune the pores. You can see there are a lot of variety of, I would say, several thousand materials already been developed. And if you can tune the nodes, inorganic part and organic part, so you can make definitely, you can create library of this kind of materials. So people always ask, what is the advantages compared to other existing porous materials, say activated carbon or zeolite. So I would just tell that these materials are simply excellent. Cost-wise, of course, they are need to be they are not that much effective, but people are trying to get cost-effective materials. But performance-wise, these materials are very good. So I give another example. Suppose this is one tour made in 2007 from Berlin to Bangkok, which is approximately 32,000 kilometers. And this car was driven by methane. So if we consider like, okay, I need to drive this car 32,000 kilometers, then how much cylinder I would need? So basically, you need 4 times of this. Like these cylinders, like these cylinders, we have loaded with like people have loaded with MOP materials, and it drives 30,000 kilometers. You just imagine, like if you without MOP, this would have not been possible, because you need like mainly 20 cylinders, which is impossible to place inside backside of a car dicky. So this is the powerfulness of such materials. So what we have done, like we have, although we have worked on storage, gas storage, but I will not talk today on that. I'm only focused on membrane-based separation, how we can do the molecular separation. You can see like we have developed some membranes, hollow fiber membranes, and we have selectively grown in situ the crystals, morph crystals on the outer side as well as the inner side of the membranes. And we could able to separate the gases, different gases like helium, nitrogen, and propane, and we could guess basically the size selectivity here. So based on the size, because these dimensions are very low, like this pore aperture window is 3.4 angstrom. So only the smaller molecule can pass and the bigger molecules cannot pass. The problem of these materials, actually, of course, every material has problems and also advantages. Like problems are like they are not very stable because of the coordination bond. So coordination bonds are prone to hydrolyze. So people thought another material that is called covalent organic frameworks. So in this material, all the bonds are covalent. But the problem is like in traditional covalent bonds, you know, they are unidirectional. So always you will get like amorphous materials. So the crystallinity or orderity doesn't attend. So if we use a reversible reaction, of course, this is possible. Like suppose in this photo, you can see if you give these bricks to a child, what will happen? They will just randomly organize. So this is typical example of irreversible reaction. So no orderity is there. But if you give them blocks, they can completely set it up. So this is the example of reversible reaction or orderity comes into picture here. And these are the advantages of these materials. I'll not read out. So far as like the material is concerned, a variety of organic reactions can be utilized to make this framework. And these are some of the methods people have already followed to synthesize this. I'll talk only the solvothermal one. So it is a tedious process and it involves several steps, and you need high temperature around 120 degree or 150 degree, 3 to 7 days. So this was a little bit difficult, and at the end you will get some powder materials. So what was our approach like to synthesize in a greener way? So we thought like if we use this mechanochemical approach, because making skip base or small organic reactions is possible by using mechanochemistry. So what we have done, we have simply grinded these things. And these advantages of this chemistry is like you can do anywhere. Like in small university where the facilities are not there. So what we have done, we have grinded it and we could see the color change, and we have each step we have characterized and we found the material, and we have tried to basically compare the material with both synthesized in both the method, and we found that of course these materials are not that great as compared to the solvothermal synthesized one, but they are decent. And like the advantages I already told, like you can change the color change, but monitor the reaction by color change. They are simple and quick, no solvent is required, and you can scale it off. So our intention was to make the membranes to do gas separation. So what we have done, because we recovered the powder, so making membranes from powder is very difficult. What we have done, we have basically used a polymer binder to make the membranes. You can see these are the membranes, so we could make bigger membranes, and they are highly flexible, so you can fold it, you can roll it, so it is possible, and the thickness is around 50 micrometer. And we have performed this membranes, we have used these membranes for gas separation of different gases like hydrogen, nitrogen, methane, and CO2. But we found that if we are loading the cork material or this porous polymer material into the polymer matrix, up to 50% we can make. After that, the membrane breaks. So because of the granular nature, and as we progressively increase the content, we increase the permeability. Means gas can flow faster through the membrane, and we could also get good selectivity like CO2 nitrogen or CO2 methane is 25 close to 25-50, which is good. So we thought like, why always we need a binder to make the membrane? Is there any possibility we can make the membrane of like this porous material by itself? Then we, after several trial, we could found a method to synthesize the membrane out of 100% porous materials. So we adopted a salt-assisted method, wherein this PTA act as itself as a binder, but after the membrane formation, you can wash it out because this is highly soluble in water. And the membrane we could cast up to 30 centimeters, 30 square centimeter, and they are highly crystalline. From the powder excited pattern you can see they are highly crystalline, and they have very high order, which confirmed from the peak study analysis. They are highly porous, of surface area close to 3000 meters square per gram. Then what we have done, we have checked the flexibility. These membranes are not that flexible as compared to like the polymeric composite membranes, but they are defect free, and they are very helpful for separate molecular separation. So what we have done, we have simply mixed both compounds, like one is smaller one, another in the like bigger one, the molecules say. You can see the smaller one can pass through because of the dimension is very less. Dimension is less as compared to the pores, so smaller can pass and the bigger can reject. So this is the beauty of this molecular sieving mechanism we have characterized. We have also like a variety of molecules we have separated from water and different solvents. So here I can show you like how it is done. So membrane is installed here, and this is the solution of vitamin B12 in water. You can see like how we can get the clean water, and this vitamin B12 size is bigger so that it can reject. So I'll move to another topic that is called energy generation. I already heard the talk of Dr. Nanda, and he has already introduced what is the process. So I'll not go into detail, but I would tell that like current energy system is based on fossil fuels, which has definitely they are depleting very fast and definite reserves. So if we see like the projection, so our energy demand will increase up to 500 hectajoule per year. However, with current pace, if we make the energy, then our production will be around 200. So there will be definitely the shortage of energy. So we need other technologies to use to develop so that we can fulfill our energy demand. So one option is hydrogen generation. So if we can generate hydrogen in an effective way, then our problem can be solved. So what we have done in this respect, so we have also done photocatalytic hydrogen production using polymer catalyst, photocatalyst. So the process I will not tell in detail. So we have like semiconductor materials, and then we shine the light. There is generation of band gap, like the hole and electron generation. Then electron will go to the surface of the catalyst and do the job. So already that Dr. Nanda already described this one, so I am not going to spend much time on this. I'll show one of our recent work. So what we have done, like we have chosen a linker. This is very photoactive linker, and we have made a framework by combining this linker with a C3 linker. So it gives rise to a hexagonal framework honeycomb-like structure, and the structure was illustrated derived from the powder excited pattern. We have modeled and we have matched the experimental powder excited pattern with the simulated one, and we could found that this is a very crystalline material. And the surface area we have measured, and we found that it is close to 1400 meters square per gram, which is pretty good. And from the UV visible analysis, we get the band gap of 2 electron volt, which signify that like this material is a semiconductor material. And with the help of a co-catalyst called nickel Me, which is a hexameric cluster, and we have used nickel. Mostly people use platinum, so we thought like using earth abundant catalyst is much better and of course low cost. So with the help of this catalyst, what we have done, like we have we could generate the hydrogen evolution up to 1000 micromole per hour per gram, which is of course very small. But this kind of material we are introducing into hydrogen evolution. So I think in future we could get a better material. And these materials are beauty of these materials are like you can use them many times because they are very stable in water, and they do not degrade. So reusability wise, this is one of the best material. So with this, I will come to the summary of my talk. I hope I could convince you like air pollution is a serious problem, and all of us should think how to minimize it. So it needs our urgent attention. And also I showed you like membrane science is how it is powerful, and it is a green approach to address such a key issues of our Earth. And material engineering is very useful technique which can be useful for our good. And covalent organic frameworks can also be used as a photocatalysis for hydrogen generation and other processes like CO2 reduction and all. So in my perception, I would say that like porous materials are multifunctional. They have different application from sensing, catalysis, storage, separation, and all other things. So it would be the wonder material for 21st century, definitely. So with this, I would like to introduce my university. So our university is like a liberal university. It's called Ashoka University, and it's a liberal arts and science university, particularly focused on research. And we have 2,000 students with us, and they are from almost all states and 27 countries. So it is an international university, and we have state-of-the-art facilities. Like we have very outstanding infrastructure, like digital classrooms, all the sports activities, AC, air-conditioned hostels, and all sort of facilities. And particularly the laboratories are like equivalent to all national or international level standard. So I would suggest you visit our website, and also encourage your student to join here for PhD and undergraduate programs that we are offering. So with this, I would like to come to the acknowledgement. So I would like to acknowledge few people like where they have basically taught me or trained me, and my co-workers, collaborators, and several funding agencies. Those funded my PhD and postdoc research, like Alexander Von Humboldt Foundation. And I have worked with in internationally reputed laboratories like CSR NCL Pune, Technical University Dresden, and Max Planck Institute of Solid State Research. I'm thankful to all of them. And currently I'm serving as assistant professor in Ashoka University. So I'm also thankful to my university. And with this, I would like to thank all of you for your kind attention. And I would be happy to answer if you any questions you have, or later on you can contact me for any clarification or anything interest to my research. Thank you very much.
Thank you very much.
Yeah. So I hope I am in time.
Am I audible? Yeah, good. Thank you. Am I audible?
Yeah, I can audible. Yeah, I can hear you. Sure.
Have you done this work in your university, Ashoka University? Have you done your work here?
Sorry, sir. Please, sir. 1 second, please. Hello, sir.
Have you done these works in Ashoka University yourself?
No, sir. Actually, most of the work is done during my PhD and postdoc. I just joined 3 months back. So
no, they have not yet that facility here.
Actually, we are trying to
so
build
one
all
of
the
presentation.
Hello, sir.
Very good. One of
Sorry, sir, I'm unable to hear you.
If there are 1 or 2 questions, anyone interested in putting 1 or 2 questions? I have a question.
Yes, sir.
MOF materials, have they been put into commercial use as a hydrogen storage?
Yes, sir. There. Yes, sir. Actually, BMW and some other companies, they are interested. So now they are using these MOF materials as a storage, hydrogen storage material, and they are putting some cylinders inside the back of the car. And so this is driven because this is very effective for hydrogen storage. So it is useful for driving car. So it is not commercialized directly the cars, but they are in a trial process.
Trial process, okay.
Yes.
Meeting as well. I will go on
Professor Misra is still chairing the session. Devasis, you have to thank
you.
Yes.
Thank you, Professor Vijay Mishra sir, for chairing the session. It's a very nice session, though there are some technical problems. So we are apologize for that. And I also thank all our speakers, especially Vishnu, because he is the student of Dhenkanal Autonomous College, and Our students will be definitely inspired by looking at him. So thank you all. And this is the end of the session 1. Now we'll start the technical session 2. So in technical session 2, Professor Bhishma Patel will chair the session.
Can you hear
Bhishma
me?
Patel.
Yeah, I'm online. I'm online.
Yes, your screen name is IIT Chem.
Okay. So very good afternoon to you all. So
Please
without
put your video on, please put your video on.
I'm trying, but somebody has been muted me probably. Yeah, okay. Now I'm.
You will be unmuted. Yes, now you are unmuted, and
Now
you
I welcome
can see you.
Sir
Okay, thank you.
Bhishma Kumar Patel.
Yes. Now can you see me over video?
Yes, please wait. Please wait. He is going to introduce you.
Okay.
Devas is going to introduce.
Now I welcome Professor Bhishma Kumar Patel to our conference. I request him to chair the session. Before handing over the mic, I want to introduce Professor Patel to the gathering. Professor Bhishma Kumar Patel completed his master's degree in chemistry from Sambalpur University in 1987. He did his PhD from IIT Kanpur in the year 1994. He has done his postdoctoral work at Max Planck Institute for Experimental Medicine, Göttingen, Germany. He has 125 publications to his credit, 3 patents and 2 book chapters to his credit. So I welcome you once again, sir. We are very proud to have you as chairman in our technical session 4. Now I request you to chair the session and take over.
Yeah, thank you, Dr. Mohanty. It is absolutely pleasure to be part of the Orissa Chemical Society. Already, since we are running late, I will not speak much about this thing, but we'll start with our first speaker, Lakshmi Narayan Nanda. I know him from his PhD days. So, Lakshmi, are you online? You can start your talk. And
yes,
I
sir.
request you to, if you can little bit cut short your talk by about 20 minutes, we'll really appreciate. Okay. So good to see you, Lakshmi, after a long time.
Nice to see you, sir. Okay, thank you, sir, for the introduction.
Short introduction of yours. Okay, you are from. Introduce yourself briefly.
Self-introduction.
Self-introduction.
Dr. Nanda,
self-introduction. Okay, so I have completed my MSc from Utkal University, and then I moved to IIT Bombay to pursue my PhD. And after that, I worked as a National Postdoctoral Fellow at Department of Organic Chemistry, Indian Institute of Science. And then I moved to Broad Institute of MIT and Harvard Medical School to pursue my postdoc. And then currently I'm working at the Institute of Chemistry at the Hebrew University of Jerusalem, Israel. So I'll be talking part of my PhD work. Can anybody, so my screen is visible probably?
Yeah, we can see you.
Okay. So I'll be talking part of my PhD work, which is the application of donor acceptor cyclopropanes to the lactone-based natural products. Basically, a cyclopropane which is substituted by donor and acceptor groups is known as donor acceptor cyclopropanes, and based on the substitution pattern, it can be of different types, like doubly substituted or triply substituted donor acceptor cyclopropane. So due to the push and pull effect of this donor and acceptor groups, this kind of cyclopropanes, they show remarkable diverse reactivity and very high selectivity for the cleavage of one of the cyclopropane bond, which is sandwiched between the donor and acceptor groups. So this kind of cyclopropane, when we treat with Lewis acid, it will form a deuterium ion, and it can used in the various organic transformations like proton-lysis trap, electrophile trap, 3+2 cycloaddition, and so many useful transformations. So most of the cyclopropanes reported in the literature, they are intramolecular synthesis. That's why it is less stereoselective, and only one bond is activated, which is between donor and acceptor groups. What we thought to incorporate one acceptor groups to this donor acceptor cyclopropane, so that all cyclopropane bonds can be activated and can be utilized in various transformations, such as if you clip the blue bond in presence of the other two selectively, you will get a highly substituted tetrahedral of furan skeleton. Now, if you clip selectively the red bond in presence of the other two, you will get a furanone skeleton. And if you clip the green bond in place of the other two reduced selectively, you will get a ring expansion product, which is basically a substituted pyranone skeleton. Now, how we can get this kind of cyclopropane? So we thought we can get this kind of cyclopropane by performing an intramolecular cyclopropanation reaction onto the vinylogous carbonate. So this particular unit is known as vinylogous carbonate. So we have studied this reaction in our lab. The diazoketone precursor was prepared from the corresponding vinylogous acid by converting the acid to acid chloride, and then it was treated with the ethereal solution of diazomethane to get the diazoketone. And when we have treated with copper ecag as a catalyst, so it gave us the desired donor acceptor cyclopropane in a highly stereo and radioselective way. And you can see it works nicely with all the substituents. And we thought to utilize this our in-house protocol to make the several reactions, like we started the ring opening reactions, and we have explored here the divergent array of synthesis of various tetrahydropyranes and furans by the radioselective cleavage of the ring opening of the cyclopropane bond by the judicious selection of reagents. So if you, for example, if you take the cyclopropane and treat with the acid, so you can selectively cleave the blue bond, and you will get a tetrahydropyrene skeleton with the oxonium can be trapped in situ. So here is the nucleophile is allyl tributyl stannine. So if you treat this cyclopropane in a radical condition, you can selectively cleave the red bond now to get a furanone skeleton. So now if you reduce the carbonyl group, you will get the alcohol. And this alcohol now, if you treat with a Lewis acid, you can selectively cleave the pink bond, which is between the oxygen is the donor and ester is the acceptor groups, and it will undergo intramolecular lactonization, and the oxonium can be trapped in various ways. Like here, you can do a Friedel-Crafts reaction. You can trap the oxonium to convert into a lactone unit, and you can another way you can just use a solvent to trap. You can trap with methanol to get a partially oxidized lactone, and also you can convert the hydroxide to the bromide and treat with a standard radical condition. So it will open up the cyclopropane in another fashion to give a dihydrofuran moiety. So our interest to use these two particular reactions in the synthesis of this kind of bioactive butanolides and butyl natural products. So these are quite prevalent among the bioactive molecules. So butanolide is basically the saturated skeleton, and its unsaturated counterpart is known as butanolides. So this kind of butanolides they have shown varied biological activity, and they display a lot of structural diversity. So they're very interesting in synthetic as well as biological point of view. So our first target was Hagenskern lactone. So these are bicyclic lactones, and this was isolated from the barconide wasps. They actually the biocontrol agents for wheat fly population in Hawaii and Queensland. So we started our synthesis by taking the commercially available octanol and hexanol as the starting material. First reaction we have performed the enantioselective organocatalytic oxyamination reaction to install the chiral center alpha to the aldehyde, and then we have in situ reduced the aldehyde to the corresponding alcohol, and the heteroatom bond, that is oxygen and nitrogen, was further cleaved by using the copper sulfate as the catalyst to get the chiral diol in hand. After that, we have done the radioselective protection of the primary alcohol, and then oxochemical addition to the secondary alcohol to get the corresponding TBS ether vinylogous carbonate. Then upon Jones oxidation, which deprotects the TBS group and oxidizes it in situ to get the in one pot fashion to get the vinylogous acid. So now the acid is converted to corresponding diazoketone, which was treated with copper as a catalyst. It gave us our desired cyclopropane in very good yield and excellent enantioselective selectivity. So after getting our desired cyclopropane, then we have converted the we have done the reduction of the carbonyl group. It's a chemo and stereoselective reduction. And then this alcohol was further converted to its corresponding bromide by using standard Appel reaction condition. And then the corresponding bromide, when treated with the standard radical conditions, it generates a cyclopropylidine radical, which radioselectively opens the cyclopropane to give this dihydrofuran moiety. And then hydrolysis of the ester, iodolactonation, and deiodination gave our desired Hagenskern lactone in very good yield and excellent enantiomeric excess. So after this, we have taken, we thought to explore our donor acceptor cyclopropane to make all these butanolide and butanolide natural products. So if you see, these are the substituted three contiguous stereocenters are there, and these two stereocenters, that is hydroxy and the alkyl group, in few cases it is syn and few cases is anti to each other. So there are more than 20 natural products of such kinds are there, but prior to our synthesis, there is only one synthesis reported in the literature by Cleve and et al., where they have explored a 5-hexo dig and 1,5 intramolecular hydrogen atom transfer and 5 endo-dig trigonal cyclization to install the lactone, and which they have further explored in a linear synthetic way to only make this zero-light C. Our approach was to make a divergent and collective total synthetic way. So we proposed that the corresponding stereochemistry can be obtained by epimerizing the C2 stereocenter. And if you do a dehydration, you can get the corresponding butanolides. And these butanolides in turn can be accessed from the corresponding lactol unit by performing an Wittig reaction by a suitable Wittig salt. And this lactol in turn could be derived from our donor acceptor cyclopropane by performing an reduce-selective ring opening reaction. So the synthesis commenced by taking enantiopure ethylase lactate. We have done the oxomichael addition, and then chemoselective hydrolysis of the ester to the corresponding acid, and the acid is converted to corresponding diazoketone, and then under in presence of copper as a catalyst, it gave us our desired cyclopropane. And now chemo and stereoselective reduction of the carbonyl group gave the alcohol, which was when treated with a catalytic amount of concentrated sulfuric acid. So it opens up the cyclopropane, that is the red bond between the oxygen and ester, and it underwent an tandem intramolecular lactonization, and the in situ the oxygenamine was trapped to give this acetal unit. And now this acetal, the lactone of this acetal further partially reduced to the corresponding lactol by using divalase. So this lactol serves as an advanced intermediate for the synthesis of all this butanolide and butanolide class of natural product. So to test our hypothesis, first we have treated this ylide with the lactol, and we got our desired olefin. It's a diastereomeric mixture, which was immaterial to us to separate. So we have done the catalytic hydrogenation to get the saturated alkyl unit. Now chemoselective oxidation of the acetal in presence of Lewis acid gave the first butanolide. Now if you do the dehydration, you will get its corresponding butanolide, which was also a natural product. So this particular strategy, the Wittig reaction, hydrogenation and oxidation was employed to get all these kind of butanolides. And particularly here, if you take ethyl phosphonium bromide and butyl phosphonium bromide, the ylide, if you treat, you'll get the epiblastomycin lactol and 2-FNX2. So these two molecules we have taken further to epimerize the C2 stereocenter, and then we got a mixture of a product which was inseparable, and now we have treated with isovalerial chloride. Here we could able to separate both the stereoisomers, and one is blastomycinone and it is corresponding to epiblastomycinone. And so this blastomycinone and antimycinone was the natural product we got here, and we also synthesized its corresponding C2 epimers. So after completion of this synthesis, we found some interesting as well as more challenging and more biologically potent natural products. Those are ancestral class of natural products. And this natural products basically isolated from the marine species. So ancestral basically a C2 symmetric molecule, and it's a first bis butanolide isolated from the nature. And it is actually the most celebrated class of natural product known as annonaceous acidogenins. So prior to our synthesis, few synthesis was reported for ancestral, but its corresponding hydroxy ancestral, it's an unsymmetrical molecule. There is no synthesis reported for the hydroxy ancestral and its corresponding acetate. So here we thought to envisage on a divergent synthetic approach to make both the ancestral and its corresponding hydroxy ancestral from a common bis-lactone intermediate. Then we thought this bis-lactone intermediate we can get by the reduction of the triple bond and oxidation of the acetal will get the bis-lactone. Now the triene, the triene unit in turn we can often by one cross metathesis reaction, and this the diene one in turn could be synthesized from the corresponding lactol by performing the standard Wittig reaction. We have tried our first reaction by treating the ylide of this pentenyl phosphonium bromide with the lactone. It gave us our desired diene. And now when we treated this diene in presence of first generation catalyst, gratifyingly, it underwent a regioselective homodimerization cross-metathesis reaction to give us our desired triene with installed both the acetals. And then we have reduced all the diastereomers. We'll get a mixture of cis trans. So we reduced to a single diastereomer. Now again we'll have this acetal unit. So this bis acetal again further oxidized by using TMOS triplet and MCPP to get our desired bis lactone. So after having this bis lactone in hand, so the next stage was ready to complete the synthesis. So we have done a bis elimination reaction to get this anceptionolide. And if you do careful treatment of one equivalent, you can do a selective mono-elimination, which completes the synthesis of hydroxyanceptionolide. It's the first enantiospecific synthesis of hydroxyanceptionolide we have reported, and thus establishes its absolute configuration. Then if you treat the hydroxy group with acidic anhydride in presence of pyridine, you can get the hydroxyanceptionolide acetate. This also completed its first synthesis and thus established its absolute configuration. So what I would like to conclude here, that we have used a single chiral donor acceptor cyclopropane as a synthon to make all this diverse array of butanolide and butanolide class of natural products from a single common intermediate in a divergent synthetic fashion. So before concluding my talk, I would like to a quote from Professor Casey Nicolò, which is a renowned total synthetic chemist, that endeavors in total synthesis provides unique opportunities to discover and invent new strategies and tools for constructing organic molecules, and they save the art, science, and technology of chemical synthesis. And finally, I would like to conclude by acknowledging my research supervisor, Professor Santosh J. Gharpure from IIT Bombay and Orissa Chemical Society, Department of Chemistry, Dhenkanal Autonomous College, for the opportunity and the invitation. And thank you all for your kind attention. So if you have any questions, I can answer here, or you can contact me later. So thank you all. It's nice to be a part of Oracle, like attending the Orissa Chemical Society for the first time. I'm happy.
Yeah, thank you so much, Lakshmi, for completing your talk well in time. So
Thank
now
you,
I'm inviting some questions from the audience. If you would like to ask some question, please do that. You can ask directly, or you can raise your hand. If there is no question, I'll just like to ask one question in your that end game, right? One of the slide, we have eliminated selectively one of the product, one of the OH group dehydrated. Yeah, this slide, this end game. Yeah, this slide. But do you get the bis elimination product also, because they are quite far apart? Yeah. Or okay, you can control this thing at, or you are doing it at lower temperature. Okay, I could see at lower temperature, that's why you're able to control. Nanda, just want your comment. Okay, I got this thing, because either elements from this or that. Are you able to hear me?
He has been muted, I think. Devasis, are you there? Can you unmute him? Looks like he's muted.
Hello?
Yeah, now it's okay. Go ahead.
Yes, sir, please.
Yeah, no, my question, I just got it, because you're selectively eliminating at one side of the molecule. Is there any chances that you get eliminated at both the side?
Yes, sir, the chance, but we are doing at lower temperature, and
yeah, that's what I thought.
Getting the starting material back, sir. Like that's what I written the BRSM yield here, like based on recovery of starting material.
Yeah. Any more questions from the audience?
Let's move to the next one. Yes.
Yeah. So thank you so much for presenting your talk very nicely, but we would have expected a little bit more from your postdoctoral work, because PhD work, we have seen this thing from Santosh's presentation, but thank you. Good luck.
Thank you, sir.
Yeah.
Maybe sometime next, I'll be talking postdoctoral.
Yes. Next time we look forward to your talk from your postdoctoral work.
Sure,
okay,
sir.
so next speaker, please, can you come online, Dr. Karmakar? Karmakar, please do join.
Hello.
Yes.
Dr. Nanda, please unshare your slides. Yes.
Lakshmi, you can just. Oh, Anirban, our that's why I'm not saying all our student only. Okay, okay. I was thinking, Karmakar, who is that Karmakar? Okay, okay, okay. So now I could see his face and I could recognize all our student only. So welcome, Anirban.
Thank
Yeah,
you, sir.
so please tell us because it had been quite some time. I have seen you last time, maybe 5-6 years back.
Yes,
So
yes, yes.
introduce because you are a product of IIT Guwahati for sure. But please tell us what about yours?
I am. My name is Anirban Kormakar, and I did my masters from University of Bardwan in West Bengal, and I have completed my PhD from IIT Guwahati. And after that, I moved to do my postdoc in Italy, in university. And after that,
Can you increase your volume a little bit? Your volume is okay.
I can you hear me now?
Yeah, now it is better. Yeah.
Yeah. And then I did my another postdoc from Chalmers University of Technology in Sweden. And now I am working as a researcher at Institute of Superior Technical in Lisbon, Portugal. And my research area is based on the development of different type of metal organic framework, development organic framework, and their application in catalysis. So I'll share my screen and start my presentation.
Yeah.
Sir, with your permission, please. What is the local time there now?
It's 7 a.m. in the morning, sir.
Okay, okay, that's fine. Okay.
Yeah, yeah. Please go ahead.
Right. So I can just
share your.
Yeah. You can see now?
Yes.
Yeah, you can see now. Yes.
Yeah.
Yeah. So today the topic of my presentation is the development of the amide functionalized metal organic framework for heterogeneous catalytic application. So first I will explain what is metal organic framework. So metal organic framework basically when the metal ion or metal cluster is connected with the organic linker and forming a 1, 2, or 3-dimensional crystalline compound that is called as a metal organic framework. So for example, when you do the reaction with a simple zinc under hydrocarbon condition, and we got a 3-dimensional porous zinc network like this. This is the first example of the metal organic framework, which is structurally characterized and reported by the Professor Moriagi and published in Nature in 1999. And this type of material, after that time, many researchers around the world start working in this area, and within very short time, in this area of research is explored rapidly, because this type of material have potential. This type of material have very good high porosity and surface area. And due to this nature of this material have shows different applications. Like it can show application in gas storage, sensing, separation, magnetism, catalysis, or energy recovery. Besides that, this type of material also have application in different more other areas. But we are mainly interested to explore the area of the catalysis by using these materials. So why we choose MOF to catalyze our reactions? Because the most of the MOFs are commonly insoluble in the common organic solvent, which is advantage as and act as heterogeneous catalyst. And this is advantage when you do the separation of the catalyst. And when you use the MOF in a organic reaction, it will be very easy to separate the catalyst from the reaction mixture. Also, for the MOF, we can easily control the pore size, because by changing the length of the linker, we can manipulate the pore size of the MOFs, and we can control the pore size. And this is a very important for the size selective catalysis. And also, it is for the MOF, it is easier to synthesize as we can easy to functionalize a MOF, or we can easily synthesize the chiral MOF by using the chiral ligand.
So this is also important in the case of bifunctional and asymmetric catalysis. So the MOF can have different catalytic active sites, because the MOF can also catalyze through different active sites. Like MOF can catalyze through exposed metal center, or it can catalyze through the ligand center. Also, some of the MOFs can grafted active organic molecules, or it can or it can encapsulate different type of nanoparticles or active organic molecules inside, and promote the reaction in a much more efficient way. Recently, some of the pyrolysis product of the MOFs can also have been used to catalyze different type of organic reactions. So our approach is mostly to develop a functional organic ligand and do the catalytic reactions. So, our idea is to introduce a gas accessible functional organic group like amides into the ligand system, and then by using this amide functionalized ligand, we can construct the amide based MOF and do the catalytic reactions. So why we choose amide ligand? Because amide have a good capability of hydrogen bonding interactions. It have both hydrogen contain both hydrogen bonding acceptor center and a hydrogen bond donor center. So it can coordinate. It can have the capability of the guest binding. So if we introduce the amide group into the ligand system and construct some MOF within this, it will provide us the more opportunity of the guest binding through hydrogen bonding interaction. Some of the recent studies shows that the amide group also have the strong attraction towards the gas molecule like carbon dioxide, acetylene, and methane, etc. And this can cause the high in gas absorption capability. Also, due to the basic nature of the amide groups, it can also act as a active site for base type of catalysis. So recently we have published our one of the work in one of the review, condensate chemistry review, and we do different type exemplified a different type of amide functionalized meteorological framework and their application in the catalytic area. So how we synthesize the amide functionalized MOF? There is a two possible way to synthesize the amide functionalized MOF. One is the pre-synthetic functionalization approach, and another is the post-synthetic functionalization approach. In pre-synthetic functionalization approach, first we take the amine ligand and then convert it to the amide linker using acid chloride or anhydride. And after that, by taking the amide based linker, we construct the metal organic framework using different type of metal ions. So this is the pre-synthetic functionalization approach. The another approach is to first we build the framework by using the metal ion, and then this free amines we can do the we can functionalize with acid chloride or anhydride this amine and construct the MOF. So do both the pathway have some advantages and disadvantages. So in our case, we mainly going to explore the area of the pre-synthetic functionalization approach, because we usually first we build the ligand first and then construct the different type of metal ion, develop a MOFs. So designing of the amide functional linkage is an important factor in this topic. So in this content, we stepwise develop different type of amide functional ligand. So first we develop a simple organic ligand. We substitute and synthesize some monoamido carboxylic ligands, and we substitute on simple isothalic acid with a simple amide-based unit like acetamide, propanamide, or benzamide unit. Also, we did similar type of prepared similar type of ligand using terephthalic acid unit, and we prepared another three different type of ligands. We also prepare diamido carboxylic ligand, like it contain two amide groups, and we also prepare these three type of ligands. And also we have prepared one more complex three amide containing ligand, amide containing ligand. This is a triamido carboxylic acid ligand. So today's topic, I mostly focus on these ligands and their preparation of these different MOFs using this ligand and their catalytic application. So first I'm going to talk about the MOFs with the monoamido carboxylic acid ligand. So when you do the reactions with this simple L1 ligand, which is monoamido carboxylic ligand with zinc nitrate, and when you do the reactions in different solvent conditions like DMA methanol formamide and methyl formamide, we got different structures. So by that do the reaction with the DMA methanol formamide and N-methyl formamide, we got a three one-dimensional structure with three MOFs with having one-dimensional structure. First one have the helical structure, and second one, compound 2 is have zigzag structure, and compound 3 also have zigzag structure. These three molecules are the pseudo-polymorphic supramolecular isomers because they have the same molecular composition but have the different solvent molecules. When you do perform the reactions with a formamide at different temperature, we got a double chain type of one-dimensional structure. But when you use the DMA methanol in presence of another auxiliary ligand, then we can able to synthesize a two-dimensional framework, which I have shown here in the as a compound 5. By performing the reaction with the L2, or when you do the reactions with the zinc nitrate in solvothermal collision, we get a one-dimensional double chain type of structure. But in presence of auxiliary ligand with zinc nitrate, we got a ladder type two-dimensional structure, which I designated as a compound 7. With the cadmium nitrate, we got a one-dimensional structure with a double chain type of network. When you perform the reactions with a benzamide, 5-amino benzamide isothalic acid ligand L3 with zinc nitrate and bipyridine, we got a three-dimensional wave-like structure. This is the structure of the three-dimensional framework. It's like a wave, and it's designated as a compound 9. And another compound we got when we perform the similar reaction with a cadmium nitrate with a 4,4 bipyridine, we got a one-dimensional double chain framework, which is designated as a compound 10. We have also prepared different reaction, different MOFs using isothalic acid, terephthalic acid system also. Like when you perform the reaction with a ligand 4, we in zinc nitrate in presence of piperidine, we got a two-dimensional zinc framework, which I designated as a compound 11. In this framework, the ligand and the zinc system forming a one-dimensional chain here, and these chains are interconnected with a bipyridine unit. But when we perform the reaction with the lanthanides in hydrothermal condition, we got a more complex systems and three-dimensional porous network, and these balls are represented as in the pores inside the molecules, and these have almost 12 angstrom by 12 angstrom square type of channels. And today we are going to talk. I am going to talk only about the catalytic application. So I'm not talking about the gas absorption capability of this type of molecules. So when you perform the reaction with the L5 ligand with the zinc nitrate, also we got a three-dimensional zinc framework like this, and this framework have the tetranuclear zinc cluster act as a secondary building block unit, and this also have the rectangular channels with a 7 angstrom by 8 angstrom rectangular channels. But upon performing the reactions with a L6 ligand with a zinc nitrate, we got a DMF. We got a just one dimensional zigzag chain, and which I designated as compound 14. And this is the hydrogen bonded structure of this molecule. Now I just little talk some about the catalytic activities of these compounds. So first we have tested the Novarangal condensation of the very simple Novarangal condensation reaction using our MOF catalyst 1 to 5. When we perform after optimizing the reaction condition, when we perform the reaction with a benzaldehyde with a malonitrile in presence of THF at 40 degrees centigrade, and
Dr.
after
Tamakar, could you please go back for a minute, because for about 30-40 seconds we could not hear you.
Okay.
Yes, for 30.
Right.
Yes, 30. Yes. From here start.
Yeah. So when we perform the reactions with the zinc nitrate with this ligand L5, we prepare the three-dimensional zinc framework, which is designated as a compound 13. And this framework also have the tetranuclear zinc cluster, which I've shown here. It's act as a secondary building block unit. And this compound have 7 angstrom by 8 angstrom rectangular channels. After when we perform the reactions with the L6 in presence of zinc nitrate, we got just only one dimensional zigzag type of chain, which I have shown here as a compound 14. And this is the hydrogen bonded two-dimensional layer structure of this molecule. Now I'm going to talk a little bit about the catalytic activities of this type of synthesized compounds. Like first, we have tested the Novarangal condensation of this compounds, and we used our MOP catalyst 1 to 5 to test these reactions. And after optimizing the reactions, we found that when we perform the reaction with benzaldehyde with malonitrile in THF only at 40 degrees centigrade, after 90 minutes we got a quantitative yield, and here is the yield of the product, and we got the yield around from 61 to 98%. In between compound 1 and 5, the compound 3 is more active and give around 98% reaction yield. And we have done the yield versus time plot, and this is the yield versus time plot. And we have also the test the heterogeneity of the catalyst, and we after 30 minutes of reaction time, we have removed the catalyst by simply filtration from the reaction mixture, and continue the reaction with a continue the reaction in the same temperature. And we did not see any yield improvement, which I show here in the as a red curve, which implies that this catalyst is totally heterogeneous and did not decompose in the reactions catalytic reaction mixture. We have also tested the effect of different solvent, and we see that the THF is the most solvent for this type of catalyst. Recycling is the one of the key important factor of this type of catalysis, because if we can do the same reaction in several times by using same catalyst, this is one of the most advantageous. So we have also performed the recycling experiment, and we here is the recycling curve, and we see we already did the four times recycling, and we see that there is no loss of activity with this system. Now we have tested the another type of catalysis by using our MOF catalyst 6 to 10, and we have done here the trans-esterification reactions of methyl 4-nitrobenzoate, and after optimizing the reaction condition, and we see that when we perform the reactions at 75 degree and after 38 hours, we got a ethyl 4-nitrobenzoate in a quantitative yield. And this is the reaction yield, and we got the yield for the compound 6 to 10 from 58 to 91%. And the compound 9 is more active and it gives the 91% yield. And we have also done the yield versus time plot and check the heterogeneity of the catalyst and the catalyst is totally heterogeneous. We have tested the different type of methyl esters like methyl benzoate, methyl 3-nitrobenzoate like this, and we got the yield from 50 to 89%. Here also we have tested the catalytic recycling, and we have seen that this catalyst can be up to 5 cycles without losing their activity. Now I'm going to talk about the MOFs with a diamidine carboxylic type of ligands. So when I perform the reactions with a ligand L and with the zinc nitrate, absence and presence of the base, we got two different compounds. Without a base, we got a zinc metallo-macrocyclic compound. This is not a MOF or a polymeric structure. This is a simple dinuclear macrocyclic type of structure. But when we perform the same reaction in presence of ammonium hydroxide as a base, we got a two-dimensional zinc 2 framework MOF, and this DMM which encapsulates the DMM molecule inside the core. And this compound we designated as a compound 16. Upon performing the reactions with copper nitrate in different conditions, we also got similar type of metal macrocycles like copper-based metal macrocycles, which is designated compound 70, and 2D copper 2-based MOF, which I designated as a compound 18. In this compound 17, in this MOF, copper-based MOF, the tetranuclear core is acts as a secondary binding molecule, and here the dinuclear battlefield type of structure acts as a secondary binding group. When we perform the reaction with this ligand, like a line L9 and with zinc nitrate and cadmium nitrate, we got the two-dimensional zinc 2-based MOF. This is the structure of the 2-based MOF, and here is the structure of the 3-dimensional cadmium 2-based MOF. Now I'm going to talk a little bit about the catalytic application of these compounds.
Nirman, try to finish it next 5 minutes.
Yeah. So I have performed the ultrasonic assisted cascade reaction. As you know, the cascade is one of the important organic reaction where we have performed two multi-step reaction in a single step. So we have chosen here one reaction like a diacetyl 1,4 tandem diacetyl Novanagel condensation reaction. And in this reaction, the acetal is directly converted to benzylidene malonitrate in a one-step process. So when you use our catalyst compound, catalyst 15 and 16, and when we perform the reaction with acetal and malonitrate at 80 degrees centigrade in 2 hours in DMF, we got the yield, quantitative yield, and we perform the reactions in 3 different conditions: ultrasonic, microwave, and conventional heating. And we see that conventional heating give only yield from 41 to 68%, microwave give 49 to 56%, and with the ultrasonic condition we got 98 to 99%, almost quantitative yield. This is maybe due to the high dispersion of the catalyst in the solution, and which increase the surface area of the catalyst and promote the catalytic activity. And this is the plot of the yield versus time of this compound. I did not explain this completely. So this we have also do different type of substrate, and we get see that the for the methyl substrate we get almost quantitative yield, but for the ethyl substituted we got little bit less yield. We have also did the recycling experiment, and this is the recycling experiment, and so we see the catalyst is recyclable up to 5 cycles without losing activity. And the structural integrity of the before and after catalyst we have checked by powder XRD, and we see the both the cases the powder XRD remains same, which indicate that catalyst is quite stable in the reaction condition. We have also performed another type of microwave assisted oxidation and novaregal condensation reaction, where we have take the alcohol and convert it to the aldehyde in microwave using a tertiary butyl hydroxide, and then this aldehyde we convert to benzylene mineral nitride using microwave condition. First, we did the reactions in separate in microwave, like when we do the separate reactions with a benzyl alcohol with compound 17 and 18, we got yield from 35 to 37. But with secondary alcohol, we get good amount of yield from 84 to 85%. And for the novaregal condensation reaction, we got the yield of 97 to 98%. So now we have do this reaction in the tandem way. So we try to do the reaction in two different methods. We take the catalyst and an alcohol and microwave it 120 degree for 1 hour, and we got the aldehyde. Then we put the mineral nitride and microwave it for another 10 minutes and get the product with a 35% yield. But when we do this similar reaction in all together in as a tandem condition, we put everything like MOF 18 mineral nitride and do the microwave for 1 hour in 120 degrees centigrade. We also get the same reaction yield. My next is talk is about the triamido carboxylic acid ligand, and this is the one example which I give you when I do the reaction with this ligand L and do the reactions with copper nitrate. We got a three-dimensional polar structure, and this is the structure of the framework. And this framework have a tetranuclear copper core, which I show here. And this compound is very active for the Henry or novaregal condensation reaction. And when you perform the novaregal condensation, Henry reactions with a aldehyde using copper MOF and with a copper MOF with a nitroethane in methanol at 70 degrees centigrade for 20 hours. We got a syn and anti product with a good yield, and we got the yield around 89% with a syn and anti ratio about 70 to 25%. And this is the recycling experiment. We have also performed the recycling experiment, and we did the recycling for 4 times, and you see the catalyst is stable and we can able to recycle without losing activity. We have also done different substrate like electron withering substrate and electron donating aldehydes and perform the reactions. And this is the powder FTIR and powder XD of this MOF before and after the catalyst, and we see the catalyst before and the after the powder XD and the IR is remain same, which indicates that this compound is quite stable during the catalytic process. And this article is selected in a Day2 transaction and published as a cover page and accepted as a hot article. So my conclusion, we have presented here 9 different example and different type of amide functional ligand, and we have synthesized different type of 1D, 2D, and 3-dimensional compounds using this ligand. Due to the presence of the Lewis acidity and Lewis acidity of metal center and Lewis basicity of amide group sites, this MOF acts as an excellent heterogeneous catalyst for large number of organic transformation like novaregal condensation, transesterification, Henry oxidation, and cascade type of reactions. And the stability and recyclability of our MOFs during the catalytic reactions also investigated, and the stability of this MOF has been confirmed by the combination of recycling tests, powder study, FTIR studies of the before and after the catalysis. And last, I would like to thank the organizing committee member to giving me this opportunity to present my work, and also I like to thank other my co-workers and my supervisors for giving me this opportunity to present my work. Thank you very much. If you have any question, please feel free to ask me.
Yeah, thank you, Anirban, for presenting your spectrum of work, starting from your PhD to postdoctoral work. Now the session is open for some few questions.
Okay. All this work started from Professor Yage's group.
Yes,
As you said, the first nature paper I
yes.
read. And since then, numerous MOF groups have started working, and uh, I also saw some people working in my group. Now, this solvothermal reactions that we carry out in a sealed tube,
Yeah.
all the time they deal with a very few milligrams of the compound.
Yes.
Yeah. And is there any kind of upscaling these reactions where we can make kg level products, because these are very powerful, very useful catalysts? So is there any kind of attempt to make kg scale products so that we can
Yes,
evaluate
because
cost and
some of the mobs we already they prepared, because some of the mobs are very stable and you can prepare in a bulk amount. And if you see in the Sigma already websites, you can see they are selling these products, mobs like copper mobs or zinc mobs in a large amount, and they are producing this in a large scale, in industrial scale. So you can buy directly from the websites, and so they are preparing these mobs. It's now it's beginning, but it's not like you can buy all the mobs, but some, especially some mobs which is very you can very synthesize in a large amount. You can buy.
mostly copper and zinc type. Mostly.
Yeah. Yes. Yes.
Any more question from the audience? Since we are running out of the time, probably we'll move to the next speaker. Okay, so I'll invite Francis, another alumni from IIT Guwahati, to come online. Francis, are you online? Yeah, Francis is again the alumni of IIT Guwahati. He did a PhD with Professor Krishnamurthy, and right now he's faculty in Manipur University. Okay, Francis can go ahead and start the presentation and give a small introduction of yours.
Yes, sir. Yes, sir. Thank you, Professor Patel, for giving me time for the presentation. First of all, I would like to thank the Orissa Chemical Society for giving me a chance to present my work. And so straight away, I will start my work. Excuse me, can you see my screen?
Yes, yes, go ahead.
Yes, you can see.
Go ahead then.
Please.
Yeah. Okay. Just a minute. Here in this work, I would like to present the work of one of my PhD students, which is more on the study of polycyclic aromatic hydrocarbons and its electronic structure property. Here, when you talk about polycyclic aromatic hydrocarbons, we are talking about carbons. And so we'll just start from the basic. If we see here, we see that carbon is the most widely available, one of the most widely available element in the surface of the earth. And it's also very cheap, except diamond. So whatever the materials we see, most of them are carbon. And if we burn here, we get charcoal, a black substance called charcoal. Now, if we take a binocular and if we just if we zoom it with the binocular and magnify it billion times, we'll see the atoms of carbon linking to each other with different structures. Now, with this carbon, the structures of carbons, if we heat it up at high pressure, then we get a very nice layers of carbon stick together. And these layers of carbon is called nothing but graphite. This graphite has very important applications, such as pencil. It can be used as pencils, like dry cells, and also dry cells, or we can use as a lubricating agents. Now, the story doesn't end here. The story is more interesting starting from here. Now, if we strip the layers of carbon into just one layer, if we manage to get a layer of one carbon, then we call this one as a graphene. Each layer, with this layer of carbon, if we roll up, we get a carbon nanotube, and from here, if we just club it, then we get carbon dots like fullerenes. So because of this, because of the ability to strip the layers of carbon into single sheet, the Nobel Prize was given in 2010 in physics. So one of the very important properties of graphene is that it has very excellent mechanical and electrical and thermal properties. So they are also called as wonder materials, just like our Wonder Woman. Now, the excellent properties of this graphene is because of the hybridization of carbons, which are which are linked together. They have the sp2 hybridization, and now if they are accumulated together, they form the unhybridized p orbitals are overlapped together, and they form the excellent situation for the delocalization of electrons. And because of this, they exhibit several important properties which cannot be found in other materials. And the objective of this work is to study the network of carbon atoms in this graphene in two-dimensional materials. So here in our institute, we don't have much experimental facility. So the alternative to study is to do theoretical study. And in this theoretical study, there are two different approaches. One is periodic boundary condition. In this study, a certain set of atoms are considered, repeating units are considered, and it is multiplied n times, means studied, multiplied 10 times or 20 times in a system. And another approach is to consider a smaller system, like a smaller two-dimensional system, like, for example, polycyclic aromatic hydrocarbon. And we consider this as a graphene, and we study the study. Here in this approach, we are considering the second approach. And here in this approach, again, there are so many polycyclic aromatic hydrocarbon. And so here we are choosing coronene. As the structure of this coronene is already shown here, which is neither very large or nor small. So we can assume that in the interior here, in this interior, the carbons are, the properties of carbons have similar properties with those of graphene. Here in this study, we are trying to substitute the coronene, just carbon atom in this coronene with heteroatom like boron and nitrogen, and we study the electronic structure properties such as band gap, stabilization energy, relative energy, and their the pi interactions. Now we know that this is graphene coronene here. In this coronene, we just label this one as 1, 2, 3, so on and so forth, up to 24. It has 24 carbon atoms. Now, in this study, we are trying to substitute one single atom with a heteroatom like boron and nitrogen. So it can substitute in 3 different positions, 1, 7, and 8. So the substitution at 1 is, we just name this one as code XA, and here for 7 is XB, and 8 it is called XC. So for the study, we are employing density functional theory with the functional M06 using the basis set 631G DP. Just by considering the coronene, we calculate the band gap, and it is found to be 3.24, which is in excellently matching with the experimental value, which is 3.29. This shows that the method of calculation that we have employed is appreciable. So using this method, we further study further for other properties. So with this method, we calculated the time-dependent density function for the substituted coronins for core X, A, B, and C. It is found that the band gap drastically reduces to as low as 0.81 from 3.24. This just by single substitution of one carbon atom by boron or nitrogen. So this shows that substitution plays is going to play a very important role for the conductivity or other electronic properties of the polycyclic aromatic hydrocarbons. So we extend our study. Now we wanted to study the pi-pi interactions of the planar rings. So this so to study the pi-pi interactions, we consider dimers of these coronin planes, coronin structural planes, where they stack on top of each other. So these dimers are characterized by interplanar distance, twist angle, and a tilt angle, then band gap and stabilization energy. So before I go further, these coronins and coronin substituted coronins form a number of dimers, means dimers which are stacked on top of each other, and each dimers have their own corresponding mirror image. But in this study, we are considering only one set of the mirror image. So these dimers, the formation of dimers follow two main mechanisms. In the first mechanism, it is followed by the substituted coronin, which is substituted atom number 1, and the substituted coronin, which is substituted atom number 7, and substituted coronin, which is substituted atom number 8. And here in this substituted coronin, which substituted atom number 8, which has the number 1, 3 odd numbers, they follow this mechanism. In this mechanism, before the two planes, the front and back planes are stacked on top of each other, the front is first twisted with a certain degree of rotation here, and then they stack on top of each other. In the second mechanism, which is followed by core XC, here in this case, before they are stacked on top of each other, the top plane is first flipped, and then after flipping, it undergoes a twist angle with a certain degree of rotation, and they are stacked on top of each other. Now, to systematically study the dimers, we are studying considering the first type of dimer, which is formed by the monomer, which is a result of the substitution at atom number 1. Here in this case, we have 3 types of dimers, which is named as core, XA1D, and 2, and 3. Here, among these 3 types of dimers, there is one dimer which is quite different from the rest. Here in this case, this is core Ba2D. Here, it is quite different from the rest in such a way that the boron on the top and the boron of the bottom one, they overlap on top of each other. So here it forms like a covalent-like bond. So because of this, it has a higher stabilization energy among this class of dimer. And because of the formation of covalent-like bond formation, it has a sp3 characterization. So because of this, it has a higher band gap compared to its monomer. Here in this case, the monomer is core Ba. So in this class of dimers, it is observed that the nitrogen substituted coronin dimers have higher tilt angle, as already I have illustrated earlier in the previous slide. And in the second class of dimers, just like coronin XA, core XB also form 3 types of dimers. In this type of dimers, it is observed that boron substituted coronin dimers have higher stabilization energy compared to the nitrogen substituted coronin dimers. Further, it is observed that because of the stabilization energy, the boron substituted coronin dimers have higher band gap compared to the corresponding nitrogen substituted chlorine dimers. This is just an illustration of the dimer, one of the dimers formed here. In the case of the third type of dimers, which is formed by the chlorine substituted dimers, with chlorine substituted nitrogen substituted chlorine, which is substituted at atom number 8. Here we get 12 types of dimers. So we are naming as core XC1D 2, 3, 4 up to 12 here. Here in this case, X in the previous slides also, X means it may be boron or nitrogen here. And here in this case, in this class of dimers, it is observed that it has the stabilization energy is drastically increased 40 to 200 times compared to the dimer of chlorine, unsubstituted chlorine. So when you see the different types of dimers, it becomes more interesting in the sense that this chlorine, substituted chlorine can form, it has high possibility to form the polymerism, the phenomenon of polymerism. And when you study the different the geometries of these dimers, we can classify these dimers into 5 types. Type A, in this type A, here the two planes are stacked on top of each other such that the atoms are overlapping. The atoms of the first plane and atom on the second plane, they are overlapping on top of each other. So they are almost just overlapping. But in the second type of dimer, which is type B, here in this case, the atoms of the first plane is stacked. It is in the staggered portion of the atom of the between the atoms of the second plane. In the type C here, the two dimers, the top dimer is just sliding on top of the second plane. And in the case of type D dimer, here in this case, the planes are distorted, and in such a way that there's a carbon-carbon covalent bond formation. And in the case of type E, there we don't have much symmetry in this class of dimers. We don't get any much generalization. We cannot get here, and most of the dimers are formed in this class. Now, just to illustrate more, here, out of several dimers we have, out of around 18 dimers, they can be classified as A, B, C, and among them, the dimers which have type A is shown by only one dimer, which is the substituted chlorine of the dimer of substituted chlorine, nitrogen substituted chlorine, which is substituted at 8 position, and it has a level 10. And among these, it is observed that type B has a most number of types of dimers. And the following slides shows about the illustrative examples of different types of dimers. Here, this is some example of type A dimer, and this is type B with a different twist and tilt angle, and this is type C, and this is type E. Then, and in the case of type D, as already mentioned here, we have twisted planes, and here there's at a portion of the twisted planes, there's a covalent bond with a bond length of around 1.6 angstrom. And because of this covalent bond formation, the band gap is increased compared to its monomer. And regarding the relative stability, stabilization energy, and band gap, overall, it is observed that the core XC11D, which is the type D dimer, becomes the most stable dimer. This is for both case of boron and nitrogen substituted chlorine. This is because of carbon-carbon covalent bond formation. And because of the covalent bond formation, it has higher stabilization energy. And because of the formation of covalent bond formation, the carbon has sp3 characterization. instead of sp2, and because of the sp3 hybridization, the band gap increased. And apart from this dimer, in other case of dimers, it is observed that with the dimerization, the band gap further decrease from substitution, and from dimerization, the band gap decrease as low as 0.52 electron volt, and it follows the order here code XAD, which is less than code XBD, and is further less than code XCD. And the calculations already we stop in the dimerization, but if we expect that with the staking of 2 or 3 or more planes, we expect that the band gap will further decrease. But in this work, we have limited here. We have stopped here, and in the future, we may plan to increase more staking of the planes. And in conclusion, we studied the substitution of coordinates at different portions of carbon atoms, and we studied the different pi interactions of different substituted coordinates, and we found that that the band gap is dependent on a different portions or different pi interactions. And it is also observed that with a different, with a several dimers, each dimer has corresponding mirror image. And it is also further observed that in type B dimers, the planes are distorted, and this distortion is because of the covalent bond formation between the carbons of the adjacent planes. And because of this covalent bond formation, the band gap increased compared to this monomer. And in the end, it's also observed that the dimerization increases stabilization energy up to 200 times, and the stabilization energy is highest in the third type of monomer. And before I conclude my talk, I would just like to introduce my group members. Right now, I have four research scholars. The first one is Amar Ningthojam, and he's working on supercapacitors, and he's an Inspire fellow. And the third is a JRF, UGC funded, and he is working on molecular switches, Dylan Khaidem. Sophie Simre is working on photophysics of biomolecules, and Sanjoy Sandam is working on catalysis. He is a faculty in a government college, but he's working right now. He's pursuing his PhD under my guidance. And this work is funded by the Department of Science and Technology, Manipur, and also by Manipur University. And I also would like to thank the Orissa Chemical Society for giving me chance to present my work. And thank you all for listening.
So thank you, Francis, for your nice presentation. Okay, so the now session is open for some question, because there are some hand was raised in between the talk.
Oh, okay. I could not notice that.
Yeah, you know, some Prabhat, or is it by mistake? Or if Prabhat, you have any question? Someone Prabhat was raising the hand in between. Are you still online? Anyone else?
Okay, then if there is no one, let me put a question. Francis, you
Yes,
are able to put a heteroatom theoretically in 3 different positions, boron or nitrogen.
Yes, sir.
Very good work, Dept calculation, fantastic. I have a few questions. Practical synthesis we carry out anytime from this flat molecule, and specifically target one carbon atom replaced with a heteroatom. Is it synthetically attempted, or is it possible? That is number one question. That is question number one. Let me finish the second question, then you carry. And this I think is D6H point group, and the starting material, it has a D6H point group, And the moment you change the heteroatom, boron is okay, it is still planar, but the moment you put nitrogen, it is no longer a planar molecule. So are these things taken care of when you consider stacking? Because if it is boron, stacking is okay, but if it is nitrogen, then the planarity is lost.
Yes.
Your response, please.
Regarding your first question, I have limited knowledge about synthesis, but according to me, the synthesis cannot be done with which is generally followed by organic chemists. According to me, I think we should follow different strategy like chemical vapor deposition, like this type of synthesis, like PVD or MOCVD, like molecular chemical or vapor deposition, this type of technique. I suppose we can do that.
Okay.
And about your second question, sir, if we see here, we can see that from the side view, this we can see from here the side view
with the nitrogen. Show me with the nitrogen.
Here, this is for the boron, and these are like this is also nitrogen, sir. So they are planars, sir. And we have already considered about the charge, even the multiplicity of the system. If we see in the coronin, unsubstituted coronin, the multiplicity is singlet. But if we substitute a single carbon atom by boron or nitrogen, we have, in case of nitrogen, we have one unpaired electron for both nitrogen and boron. So we have already considered that multiplicity. So when we do the calculation, we consider that for the monomer, it is a doublet instead of singlet. So when you do the calculation, it is still planar, sir, and it has, unlike what you said, it is a planar, and the both nitrogen and boron, they have a sp2 hybridized atom. Like you can see from the structures, we can see here, I can show this for the boron nitrogen boron substituted here, it is planar, quite planar. And this is for, again, this is for boron, and this is for nitrogen. So I don't know whether I can clear my your doubt or not, sir.
And it's okay. I mean, if it's just like pyridine, you have just replaced one carbon with a nitrogen, and if it sits there with a carbon nitrogen double bond, it can be planar. That's what I'm asking. Is it when you replace, it is possible that the carbon nitrogen bond can have a single bond, then it becomes sp3. If it is sp3, it is no longer planar. That was my concern.
Yes, sir. But here it has a sp2 characterized, sp2 hybridized. Yeah, and in monomer.
Okay.
Okay, if there are no more questions, let us thank Francis and all the three.
Professor, can I ask one question?
Yes, sir. One more question. Please go ahead.
Yeah, this is Aditya Panda Francis.
Yes, sir. How are you, sir?
Just one doubt, the idea behind, having these tagged ones, I think it could go towards the crystal structure. I mean, when you go towards the crystal, they could be stacked like that. And have you looked at instead of dimer, like one above the first one, have you tried the third one or the fourth one? I mean, they could be stacked like that also. What do you think like that would give?
So that we have not tried yet, sir. So we are just so far we are limiting to 2 layers, 2 planar molecules, sir, stacking on top of each other. But in the future, probably we'll extend to 3 layers. Systematically, we go to 3 layers and 4 layers. We'll do that. Actually, the objective of this study is that we want to study these substituted polycyclic aromatic hydrocarbons as electrodes as a application as electrodes. We want to do that. And in the process, we found out that we have several dimers, and from these dimers, it can show different polymorphism properties.
All right.
Yeah, and in fact, there was last year in 2019, there was a paper in Nature Communication where coronin has it shows polymorphism property here. So we further extend our property study.
Yes. So just one question with regard to this. So this stabilization energy that you talked about between these stacked ones, is it purely pi or there is something else there also. Is it a purely pi stacking or there is some other interaction there?
You mean the relative energy? I mean,
no, that you know, the
between the layers, what is the distance? Is it like graphitic layers, or that's the question, I suppose.
These are layers,
yes.
But here, except as I told you, there are 5 types of dimers. Except in type D, they have like like covalent bond formation between the 2 planes.
Yes, I missed this slide, and now I see it. Okay, all right.
Yeah.
So that this would be very interesting for for you to just to check like how much total stabilization energy can it be divided into different parts. Like so that is a covalent bond there, and then if there is a pi interaction energy also here, and how do you divide it into different?
Okay. Yes, sir. Yeah. Thank you for your advice, sir. So we are not looking to that, but here we have pi interaction as well as like covalent interaction here, especially in this type of dimer. But in other types, these are mainly these pi interactions.
Yes. Thank you, Francis. Very nice.
Thank you, Francis, and thank you all the speakers for finishing their talk on time. And now I hand over the session to the organizer. And thank you so much for giving me this opportunity.
Thank you, sir. Thank you very much. You have nicely managed the session. And I also thank all the speakers. They have stick to their times. So I'm again thanking them all. Now the technical session 4 has come to an end. Now we'll start the panel discussion, and I request Professor Ashok Kumar Mishra, IIT Madras, to chair the session. Before handing over the mic to him, I want to introduce Sir, and I am very much thankful to him that he has managed yesterday very well and sent a write-off immediately to me and the President OCS. Thank you, sir. So Professor Ashok Kumar Mishra completed his master's degree in chemistry from Delhi University in the year 1980. He did his PhD under the guidance of Professor S.K. Dogra at IIT Kanpur. He has done his postdoctoral research with Professor H. Shizuka under the Monboso Scholarship Program in Gunama University, Japan. He started his professional career at Sambalpur University as a lecturer and subsequently moved to IIT Madras. Now he is working as a professor and also as additional charge as Dean Academic in IIT Madras. He has conferred with Professor Wahid Uddin Malik Memorial Award by Indian Council of Chemists 2013 and Acharya P.C. Rai Memorial Award by Indian Chemical Society in 2012. He has more than 100 publications and several patents to his credit. We are very much fortunate to have you, sir, and sir is present totally 2 days fully. So thank you very much. Now I request Professor Mishra to take over the meeting.
So thank you very much, Dr. Mohanty. So Professor Samal, what would be the topic of discussion today?
Yeah, we have Professor Bhishma Patel with us, and I request him to be in the panel. There was a kind of communication gap. Earlier he was in the panel, then when he was moved to chair a session, somehow by accident his name got deleted. But he was originally in the panel. So sir, we shall include Professor Bhishma Patel as one of the panelists. Today, we just, because there are new viewers here, some new viewers, in addition to what we have to concretize what we decided yesterday, how to make it convenient, how to make research and in our undergraduate and postgraduate colleges, how to change this scenario and make it convenient for the students and the young researchers to continue research. What way we can advise OCS can come forward and make it easier for them. So almost like the same topic that we had yesterday, but we have to.
Sir, namaskar. Sir.
Yes, Dr. Pradhan, Professor Pradhan, we missed him yesterday, but today he's there in the panel.
Yes.
And, Madam is there. So over to Dr. Professor Misra.
So, maybe please let me know the new panel. Vishnu is there. Then who are the other people?
Professor Pradhan is there. Professor Pradhan, Narayan Pradhan.
Narayan Pradhan from ISCS
Yes.
Kolkata.
Of course.
He's from ISCS Kolkata. Yes.
I'm there. Professor Smruti Rekha Das is also here. Professor Paltosh Mohanty is here. And Professor Nigam Das has told me to join within 5 to 10 minutes.
So, Professor Smruti Rekha, was Professor Smruti Rekha Das yesterday? She was not there.
Smruti Prabha Das.
Prabha.
She was there. Yes, she was there. Today, new faces are Professor Pradhan and, of course, Professor Patel.
Yeah, only. Okay. Okay, so let me, since there are new members who are. What I will do is, I will briefly summarize what we discussed yesterday. And in fact, I made a summary and I had sent it to the organizer, Dr. Mohanty. So basically, the idea was how OCS can play a supportive role in chemistry teaching and research in academic institutions of Orissa, especially recognizing the fact that a very large number of institutions in Orissa have fairly, the facilities are fairly inadequate in terms of manpower, infrastructure, and so on. So a few things that emerged yesterday was that one is for, let us say, institutions where there is undergraduate teaching primarily and some postgraduate institutions where the manpower is absolutely low. So meaningful research is almost impossible to carry out. But what can still be done is OCS can focus on providing educational support. Sometimes teachers are not available there in terms of conducting online maybe lectures and classes, which can be recorded and circulated if necessary, but topics which are syllabi relevant, so that it will be directly relevant to the students. And in fact, one of the reasons for this could be that, as you know, as of now at least, OCS has a very large number of very highly experienced and knowledgeable, competent senior teachers. And their support will be extremely invaluable towards this. The second one was it was observed that the undergraduate chemistry honors level curricula are uniform throughout the state. But at the postgraduate level, the curricula appear to be different in different institutions. A kind of a rationalization there could be good, in that it can be rationalized to the extent possible and align itself with the kind of a national curricula that are existing in good institutions. So towards that, OCS can coordinate the effort. Then there were a couple of other things that were discussed. One was that forming clusters. For example, given the limited research opportunities, if some institutions with the physical proximity of each other can come together and form a cluster and keep on accessing facilities in different institutions, so that there is some kind of a synergy there. And our OCS members in these institutions can probably form some working groups there and carry forward this idea. OCS can help them there. The other one was, basically, it's a good idea if OCS could support some kind of a mobility for students and some of the faculty who are starting their research in small places. A mobility towards going to a better organized, better institution, either within Orissa or somewhere outside Orissa within India. If at least the travel part can be supported, something can be then that will be useful. The funds position of OCS may or may not allow, but it is some idea which can be taken forward, some endowments, if possible, can be created where this support can be given. So these were some of the issues that were, quite a few issues that discussed. In fact, it was over around 40 minutes or so. These are probably the ones that stuck to my mind till the end. There may be some other things which I have missed out somewhere. But other than that, this is the thing. Basic broad theme is then the role of OCS in supporting chemistry research and teaching in academic institutions of Orissa. So Professor Patel and Professor Pradhan, if this is sort of, if this theme is now understood, I would start with both of you. With Professor Patel first. Would you give your input?
Yes. So far the Orissa Chemical Society is doing a really wonderful job organizing the conferences, both the midterm and the annual conference in the various places in the Orissa. But still it is not able to reach to some of the colleges, I feel. Because like some of the college where the particularly PG programs are there, they should be, at least some of the teachers should be participating or students should be participating. Like for example, the Sundar God College. I'm just staying less than a kilometer from the college, but I never had the opportunity to visit because all the teachers have left now. Okay. It is at least if I could visit, once they called me in the botany department as a chief guest of all this thing. But if all the head of the department, if they can invite their alumni, so many glorious alumni are there from the Sundar College, but present student, I don't think they know any of them. Because if at least we can get a chance to interact with the student, at least they will get definitely some motivation. Like with the online platform now, so many seminar and various activities can be arranged. Recently, the Gunpur College arranged some green chemistry symposium, and where the participation was very good actually. And I was one of the speakers, and I could see the enthusiasm in both the teachers and the student. So similar such can be arranged. So we should have a network of all the head of the department where the particular PG programs are running, and they can be also told that who are the potential speakers. Suppose if we get to visit to my locality, then I can visit those places. Okay, so I can tell my program. And secondly, because many of our students are probably in the PG level, they are not aware of the various summer academic fellowships, because all the 3 academics are now they're taking a huge number of students. So if the student can be encouraged and motivated, so they can also apply for the various kind of fellowship, and they can work, get a chance to work in a better institute, and they can get the exposure. Yeah, so Dr. Pradhan, you can just give your input.
Can you hear me?
Yeah, sure.
What I was thinking about the idea comes, what Professor Mishra was talking, idea comes if you provide them the literature update. Okay. So that is the reason we need to provide some literature update. That is one of the things that can be accessible to the students in the different colleges. So that Professor Patel was talking that some of the students can be migrated to the institutes where we are. They can get the lot of references, so they can copy it, they can read it, they can generate some research level idea or something idea that can be executed by in many cases. So availability of the literature update is something we need to think about it.
Okay, then Smriti Prabha Madam, would you add anything to what we discussed yesterday and today? Are you there, Madam?
Yes, sir.
Yes.
Sir, namaste. Thank you for
Okay.
calling me.
Yeah.
Actually, yesterday I am told that what are the problems in government colleges, but after seeing the 2 days program, I actually appreciate the effort of OCS and Dhenkanal College, so that they made us aware of many things which we are not knowing. Then it will also be helpful for the students if they will participate. But 2 things are very essential for colleges, sir. One is the teaching learning process, and second is the research. Because after some teaching learning process, we can proceed to the research. So I think so many knowledgeable persons are in OCS. Why we are not attempting to have some online video recording on the lessons, on the syllabus of the UG and PG, for which the remote colleges are lacking and they are not being well taught there. So we can help them by having some online teaching coaching process, or you can provide them some video by creating this CD, etc., so that all the knowledgeable persons present in the OCS can contribute their knowledge with the remote colleges and the students. And obviously, I think President has yesterday told about the unavailability of the teachers in the colleges. Therefore, many requirement of the teaching position is not possible. So that can be one thing. And this type of meeting, this type of webinar also help you in research. And as Dr. Pradhan said about the literature, if the student will learn all these things, then they will be interested to learn the literature correspondingly, and that will also help you.
Thank you, madam. Is Professor Delikar there today?
Sir, can I, Professor Misra,
Yeah,
we
yes,
have now with us Professor Nigamananda Das,
Okay.
Utkal University. He has just joined.
Professor Das, welcome. We missed you yesterday.
Thank you, sir. Actually, I am outside. Anyway, I'll talk for 5 minutes, 2 minutes,
Yeah.
3 minutes.
Yeah, please.
Today, I have listened first 2 lectures. I definitely have listened. The one thing I want to add is this type of lecture is good, a series of lecture. But only thing is that I want to say, if we want to add something for the colleges, particularly the affiliated colleges and other colleges. So as a CBS course has been introduced, and one of the component is project. So can we organize some kind of program where they say we can how to write a project?
This is for the undergraduate level, right? For the BSc level.
Dissertation, particularly all problems. I'm talking about undergraduate. The project work is compulsory now.
Okay.
And in 6th semester they have a project. So can we have some this type of program where we can at least say how to choose a project, what will be the criteria, and how to write the report, because project report is also important. And many of our faculty, those who are working in government college or private colleges, they are not acquainted this type of how to write a project, because most of them have actually are not taught how to write a project. So that's why can we have a program like this?
So
that
sort of creating guidelines.
Say something.
Will it be like creating guidelines and formats and so on?
Yes, guidelines. So we have proposed a guidelines, particularly in CBCS course. We have proposed a guidelines. At least we can discuss little bit more, so that at least all the faculty will be get acquainted that this is the mode of writing, and we can propose a formula how to write. We can have a plan or like that. We can write like this. Otherwise, those who are actually writing a project, if you go through the project, it is not a project. Just they are copying something, not in order. Everything, the reference style, everything is totally in a mess. So at least we can give a total what are the guidelines how to write. So that we can one thing we can give. And
thank you,
one more thing I want to whatever practicals. Can we give a video type demonstration that this type of practical can be done, so that at least student can see that this is how the practical can be done. And many of our faculty also have not done this type of practical, whatever actually introduced in CBCS. So that is one thing we can add.
Actually, I have a question here, Professor Das. Maybe you will be knowing, and some others senior teachers will be knowing. When this new curriculum was introduced for BSc honors level in Orissa, was there not a kind of a plan to create these videos with funding from government of Orissa?
Yes, right now we have also fund, sir. Right now the local university has some fund, and they have made some video for theory classes, but unfortunately they have not done anything for practical classes. I am talking about practicals, because even we have done almost 15 different programs for undergraduate teacher as academic training for CBCS course, and almost we have devoted 2 days for practicals, but it is not enough because in Odisha almost we have more than 1,000 colleges. So getting every colleges it is difficult. So that's why if we have a video type of or something, some sort of practical YouTube or something like that. So at least we can distribute among all, and they can also at least perform the practicals and other things. So that will be a great benefit to the student as well as the faculty, those who are actually teaching right now, because most of them actually have not done this type of practical in their lifetime also. And those who are actually very fresh, they have also not done in their, So this is one thing I can add. Other things are okay, but this thing we will see that at least this thing is done.
Actually, okay. To this,
can I speak something?
May I know who?
Can I speak something?
Professor Pradhan. Yeah, please.
As Professor Das was talking, practical is practical. One has to do in hand. If you make in video or something, they will little help. You need to make some arrangement to do practical, either for a teacher or a student. Okay, so
No,
video demo
I
is
am talking that how to do that. Many of them are actually not knowing that how to do it. So at least for teacher, at least we can give them. So teacher will be benefited first. Then they will do their own in their laboratory or in.
A kind of orientation program for the teachers.
Colleges.
We discussed, yes.
Can I tell something? Sir, can I tell something?
Yes.
Yes, madam.
Sir, actually, we have planned and approved one faculty capacity building program for 15 days in Ravensar in the last March. Actually, it was planned and sanction was done from the university for 15 days starting from the April 2. But because of the pandemic, we have postponed that. I think when situations will be better about these hand-on experiments, which are there in the curriculum of undergraduate courses, and some computational chemistry coaching or teaching, I can say, were being planned, and it has been already in there in our program. I think when the position will be improved about this pandemic, then we can have that. We can also extend that to 1 month. It was actually planned for 15 days, and 3 lakhs rupees already has been allotted by the university for that.
So, actually, my just extension question to Professor Samal, will OCS have a role to play in this, and if so, how?
Yeah, in fact, for that thing which Madam is talking about, I went to Ravensar University maybe in February, 1 month before, and I talked to the then head of the department, and they told me, fervently requesting, sir, a course has been introduced, and we are getting many telephone calls, many inquiries from many colleges, that we do not know what is this course, and we do not know how to do the practicals ourselves. I mean, the teacher's plight. See, we frame a curriculum and we do not properly plan it out. It all becomes a mess. So there are about 30 experiments in that particular curriculum, and the teachers, they do not know how to go ahead with those things. So OCS can organize webinars and trainings and all that, but Ravensar University has agreed to do the practical. They will demonstrate the experiments in the labs in physical meetings. So that was already planned, and I think government has also permitted, and because the teachers have to move, they are in government colleges, so they
can I add?
Yes.
Sir, World Bank, whatever fund has given, it is given to almost all universities.
Okay.
And under that, there is one component is academic training. Our university, we have also conducted one program for chemistry, and 2 days we have devoted only for practicals. and we have demonstrated almost all the practicals, whatever actually given in the CBCS course, which are new to them. That we have demonstrated. But we have only done for 50 colleges. It will take almost 1 year or 2 years
Can I speak?
to complete all those colleges. So in that respect, we can develop a video or this type of work. Then it will be very beneficial to them that we can give them all at a time. Otherwise, it will take long time to complete all those colleges. So that is my opinion. And at least we can have some fund under World Bank. And since I am the coordinator of World Bank, if a proposal can come from the OCS or something, at least we can see that we can give them approval from the vice officer that yeah.
Thank you.
Oh, that will be good. That will be really good, no?
Money is always interesting.
No. Money also you need a workplace because OCS doesn't have a lab of its own. So that's right. That's a very good idea, Professor Das.
Sir,
we can do video recording of the hand-on experiments.
Yeah.
Yes. And then it will be circulated.
Yes.
So what I suggest is if this, let us say Utkal University or Ravenshaw University, if they can sort of partition the number of experiments in such a way that some experiments are sort of videographed at Ravenshaw, some experiments at Utkal, it could be a good idea, no?
All experiments individually we shall video it.
Sir, we actually plan to individually do the experiment with 60 participants, and we have also planned to have a video and audio recording of the experiments.
Perfect.
So that 15 days will be a demonstration for all the colleges which we were not able to participate in that.
So if all the 60 can be videographed in 2 different places, that will be like 2 different books for the same topic. It will be wonderful.
We have planned for that.
Yeah.
I think, sir, there is a question from Dr. Priyaranjan Mahapatra. He wants to say something.
Yeah, Dr. Mahapatra, please.
No, same thing, sir. When Ravenshaw or Utkal University is organizing such demonstration class, so I am requesting them to have a video recording and we can upload in the OCS website so that those colleges who are not able to participate.
Absolutely. I think they have to submit one copy to the government also, but we can also get it. It's actually free education material, so I think anyone will be happy that we upload it and we make it accessible to all.
Actually, we have got a permission from the higher education also regarding that.
Oh, wonderful. So things are going on well, then. That's really good.
She has a very good contact with the government, so she can do many things.
Oh, yeah. So,
sir, can I have? I have just one question for Paritosh. Paritosh said a very beautiful thing yesterday.
Yeah. That's right.
We know that we pick up some 10-20 students per year, and then we allocate them in different research centers, established research centers of the country, and then we provide them the transit cost.
If that can be done, that is a good idea. So what Paritosh was talking about is some getting an MOU and so on. It will not be really necessary. It's just a request letter to the corresponding heads of the department, maybe more than enough for most of the institutions. If necessary, we can enter into some agreement, but it will be a very good idea if some funding support, at least the mobility, the transport support can be given. And local hospitality, if there is any OCS member anywhere, they can take care. In a hostel,
yes, sir.
Accommodation is not a very big thing.
So that that point which Paritosh said, we also discussed with all senior teachers. At least last night I called several of them, and they said that over a period of say 5-10 years, if we can help around 100-200 students with advanced input, they will. It will be really a good thing.
But maybe what we can do is make sure that the students are truly from sort of underprivileged colleges, where there is actually
there has to be a need. Selection procedure.
Actually, I have carefully written that statement in the summary that I had sent.
Yes, I read it.
So that's a good idea.
Right.
So then Paritos is only left now. Dr. Paritos, would you like to add anything?
Namaskar, sir. Actually, I have few points to actually mention. I think Patel Bhaina, I think what he has said, that's really a fantastic thing. I think OCS can take the lead. Well, I can probably add what he has said. I would support that point. Every year I spend 1 month in my hometown at Baripada. There's only one occasion, I went to MPC college or, this North Orissa University when Sarat Bhaina was there to conduct his students for, this Bhai examination. That was the only time when I visited there. I don't know many people there, and even I think people in the university they don't know me. So I can guarantee that I can spend at least more than a week, or at least I can discuss or interact with the students for 8 to 10 days, because my in-laws house is in Baripada, so I spend at least 8 to 10 days in Baripada definitely. And I think it will be a really good opportunity for them, and it will be a good opportunity for me. I can at least spend a week, spending time with the students, teaching something if they want, or anything. I can actually dedicate that time for them also. This is first point which I can tell. And OCS probably can actually take a lead to mobilize this. Somehow we have to frame out how or check out how we can actually do it. And second point I want to add what Smriti madam has told already. Let's say we have a framework of undergraduate courses. Individually, I think we have so great teachers who have retired. I think yesterday also Mr. Sir told the thing, and everybody has the same opinion. We have really a good pool of teachers. I don't expect even in next many years whether we can get such teachers in the state. So we should not miss the opportunity to have their lectures, video recorded and put it in the OCS website. We should take this as the priority. We can take care of the curriculum first, and individual chapters, whoever is actually ready to take all the senior, the retired teachers, they can actually teach, and we can video record, and we can put it as it is almost like a jewel thing which we can keep in the OCS website. It is not only Odisha. I am sure we may find that people or students outside the state also, they can access this, because I know our teachers, how good they are. Even when I compare with many teachers in many reputed institutions, I still can actually rate our teachers were way ahead than many of the teachers that I have seen. So even I would not surprise students from IIT, they would browse the website of OCS to learn something that I cannot even avoid that thing, and I can expect that very easy. So resources putting in the website of OCS, I think that should be really first priority. That is what I feel. And I think the OCS website, we should make something so that the OCS website, now everybody has a mobile phone. All the undergraduate students, postgraduate students, they have a mobile phone, they have internet facilities. So we should make something so that they should know also whatever they wanted that is there in the OCS website. Not only the lecture, the question answer. Let's say what type of question they can expect in the exam. Sometimes now actually the world has changed. Students are not actually studying in the point of only learning something. There are few students who are learning how to, or at least studying how to learn new things. There are many students who wanted to pass in the examinations. So we should make actually question answer and all sorts of things, that type of resources in the OCS websites, so that I think we should make OCS website very busy, so that we should get a complaint from Sardar sir ki OCS website of class ho gaya, we need an upgrade or we need an extra space, something like that. That can actually sort out a lot of things. And I will come to the third point. I think what we have discussed yesterday, what I have actually opinion yesterday also about generating fund. Once I think sir has already mentioned yesterday that we are in the process of getting everything done. Once we have actually this 80C or something like that income tax act, if we can have that, I think we can really generate some fund which can support 10 to 20 students easily, because nowadays industries are also, they have a particular fund which they can donate to many organizations. And I think this year they're probably not giving, but from next year or once this COVID situation will be over, some of the industries, I think we have several industries in Odisha, like many coal mines, many mines are there, and related industries are there. So we can get a chunk of fund. I think we don't need a lot of money, only a little bit of fund can help us also to take care of that. I think funds should not be really a big problem if we all try to mobilize or try to approach people. So these are the points actually which I wanted to add, what I have said already.
So thanks then. And then so our panel opinions are over. Yeah, then now Professor Samal.
Just may I just take your permission, and I request Dr. Mahapatra to share OCS website, the current website. Can you do that, Dr. Mahapatra?
Just a minute, sir. I'm
There is something I need to show, the provisions which are already there.
Sir, 1 minute. I'm talking with the mobile, so I'm just opening the website and I will show you.
I do not know how to do it otherwise. So in the just briefly, I'm telling you, on the OCS website recently, we have introduced, not recently, about 3-4 months back, career assistance cell. On the very top of it, you can see career assistance cell. That's purely the same thing which we want to do, whether we upload video or questions, all those provisions are already there.
Actually, yeah. Now,
Yes.
Professor Swami has any other additional input this today, Professor Swami? Sarath?
Sir.
Yes.
Exactly, sir. What I told one thing, I can tell to Priyanjan to include in the resolution.
Yeah.
That regarding, sir, when you are teaching, all of you are teaching when the PG students, we have found a lot of gaps between the graduation level and the PG level. Also some overlappings. That something they have read, again that is in the PG course. That is why yesterday I told, and most of us are in the different, the board of study members of different university. The graduation course and should be framed at the college level according to what is available in the PG course, by which it will be correlation. And this is first point. Second point, what Dr. Paritos told, exactly that is the very good idea. All the ideas will be recorded, and along with that we told that upload of the videos from different from the inside Orissa. I can propose that many of our Odisha scientists working in outside of the Odisha, that Naran Pradhan is doing good work, Paritas is doing good work, many Deva also doing good work. Let them some idea of the by which they can upload in the Odisha Chemical Society platform, by which what Nigamai told exactly that regarding the project at the graduation level, they will get some feedback to frame some methodologies for the project work. All these things, if it require, if it will be, that means all we should focus in the website of the Odisha Chemical Society with some videos or practical purpose by which the student will be motivated for the project. And yesterday, sir, also I told to make a cluster of different parts of the Odisha.
So all that I have made it already made a summary.
Yes.
Last night I sent, but I did not get the emails immediately, so I just sent it to Dr. Mahanti. Yeah. That is that.
I shall, sir, briefly respond to Professor Swami's statement. In fact, this undergraduate courses being repeated in master's courses is not a new story. It has been a subject of discussion for the last 30-40 years. It was pointed out in several occasions that in most of the undergraduate colleges, in many undergraduate colleges, the level of teaching requires a kind of brush off. You need to, once you get into MSc level, when all students are put together, they are from different locations. So even if it is thermodynamics or chemical kinetics, we do it all over again. That is the reason, because the input is not same for everybody. Many times we discuss that we drop something and put it only in undergraduate and rest in postgraduate. That has not been possible so far because of this reason.
So shall we see the website now?
Yeah, Dr. Mahapatra, please click this career assistance cell. First, could you go to the home? Just click home and scroll down, please. Click home page. Home. Click home.
Devasis has shared.
Devasis. Okay.
I have shared.
Okay. Click home.
I'll
Okay.
assistance cell.
Okay. 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 So it opens a scroll down. So you can. I heard about postgraduate level or undergraduate level questions. So details of how you submitted questions are here. What kind of questions you put, and the detailed guidelines are given. You can view a sample question. Can you click here? Are you a student? If yes, view questions here. Just click here. Yes,
orange color.
ये जो HCRE लिखा है सेटा को देखो सेटा को क्लिक करो
अच्छा good sir
yes click view questions so it will open I have put a sample question so you just click download question it will open and you can see sample questions are already there okay so maybe any level, +2 level or +3 level, you put questions, the detailed guidelines are there. You have your answer, you have option to discuss directly with the student. Anybody can interact with you if you have given your WhatsApp number or email number. That is done. So we can build it up, but next, would you go to the home page again? Devasis, go to the home page. Please go back to home page. Delete this. It काटी दे लीजिए कोटी जो ऊपर right ऊपर top रे काटी देता है. এটা PDF file. This is a PDF file. Cut it. ये जो 5 F5 DD3 लिखा है तो काटो. Quit opera. Okay. Go back again. Because I want to show you, sir, regarding this. There was a comment that there are many distinguished scientists, Professor Pradhan. We really, I mean, all other who are doing very great science. We are very much proud of you. And we had a discussion with Professor Mishra that, and it was in fact his idea that we would have career counselors. So that provision is already there in the website. We shall put like Professor Mishra or Professor Narayan Pradhan and all of you who are doing wonderful research as career counselors. So where students can directly reach you, you can give them any research idea or you can invite them to your lab or anything. So Devasis, again, share you go to home, click home and scroll down. Scroll down. Scroll down. Go down. Yes, go down. Go up, please.
Zoomer meeting. Zoomer meeting कशा असते ते?
Here there is called career in chemistry. Click करो it. Career in chemistry. It's all
Google Meet.
Click it. Then you can see career assistance again, and here there is career counselors. Click it. Click करो.
माहिती का तर PUBG बंद झाली नाही.
So we want to build this up. It is automatic. We can. You just allow us. Like I want to add Professor Mishra. I want his permission. So if give us permission, we shall put the names of all the working inside Orissa, outside country. The career counselors will give option that any student can reach them, advise them, or can invite them to kind of short-term summer program. All provisions are already there. We just have to use it.
मग आता इंडियातल्या लोकांची ग्लोबल व्हर्जन मधून अकाउंट
Professor
ट्रान्सफर
Mitra.
इंडियामध्ये ट्रान्सफर करायला लागले.
म्यूट कलो आंको
all of you to kindly mute.
admin रो म्यूट करा. admin रो म्यूट करा.
I have muted all. Now kindly unmute yourself and tell, sir. Anyone?
Sir, you have already started, I think, a lot of excellent things. Only thing is that it should go to the students now. Students should know that all the information are there. I think you have done already excellent job.
I would like to respond, and if nobody minds, I will tell you a sad story that bothers me a little bit in this last 2 days conference. Please do not mind. We are all friends. How many of us have seen anybody from our universities and NIT? How many teachers participated here? Just answer this question. Why this? Why no representation from North Orissa University or Ravenshaw University, apart from Madam? No from Utkal University, no from Brahmpur University, no from NIT Rourkela, not even a student. I do not know, at least no faculty has come to this. So if we do not honor our own organization,
yes, sir.
We do not, propagate our own culture, who is going to come and help us? Please excuse me for saying something true, and please carry forward this message. We are not doing anything for anybody. We are doing something for ourselves. Our state is in a very sad situation because of some kind of mindset. There was a lecture sometime back. Professor Patel was giving that lecture, and I asked him, is there any change in mindset of Odia students, those who are going to work outside? And he said, no, it is, something is different, something is wrong. So when we ask the teachers to come and get practical training, and when they go back and they find in their laboratory, there is not even test tube, what experiment they can conduct? One teacher, no laboratory assistant, no demonstrator, no test tube. How can he do these advanced experiments? So, and really, sir, it's a very open platform because everything is being recorded in YouTube. And I'm telling this, kindly go back, and I am requesting in folded hands, please attend these kind of deliberations and tell it to your students that it is necessary that we must rebuild our culture. We help the state have an image in the national arena. That is the first thing we have to do. ତେଣୁ ମୁଁ ଯେତେ ୟାକୁ ୱେବସାଇଟ୍ କି ବାଗେଇକି କଲେ କ'ଣ ହବ? ଯଦି ସାର୍ ମାନେ ନ ଦେଖିବେ, ସାର୍ ମାନେ ତାଙ୍କ ଷ୍ଟୁଡେଣ୍ଟ ମାନଙ୍କୁ ନ ବତେଇବେ, କିଏ କରିବ? କୁହ ଦେବା ପରିତୋଷ, କୁହ ମତେ। ମୁଁ ସମସ୍ତଙ୍କୁ କହିଲି ଯେ ପ୍ୟାଣ୍ଡେମିକ ସମୟରେ ପିଲାମାନେ ହଇରାଣ ହଉଛନ୍ତି, କ୍ୱେଶ୍ଚେନ୍ ଦିଅ। ଯିଏ ଯାହା ଜାଣିଛ, ୟୁ ଆର୍ ସବଜେକ୍ଟ ଏକ୍ସପର୍ଟସ, କ୍ୱେଶ୍ଚେନ୍ ଦିଅ। ଯଦି କ୍ୱେଶ୍ଚେନ୍ ଟାଇପ୍ ନ କରିପାରୁଛ, ହାତରେ ଲେଖିକି ପଠେଇ ଦିଅ ମୋ ପାଖକୁ। I will put it in nice print and then students can see it.
Sir, ମୁଁ ଗୋଟେ କଥା କହିବି। Yesterday, the first statement I have made, research is a culture. It is actually, it takes generation to build something. And yes, I think we are in a really bad situation now. It should be made, and it should be, I think it will take really long time. It's not that we can make it in overnight. I think last maybe 20 years or so, I think things are not right. Even I have asked Devashish also privately, are the colleges getting fund to procure reagents and glasswares? Are there laboratories also? Because that was also my concern. Even if we are giving whatever training, practical training to whatever teachers, if there is no laboratory, if there is no fund to procure any chemicals or reagents, what is the need? Even what is the reason of actually giving all sorts of training? So we have to understand that also. Although I have not visited any college recently, but what I presume, the way things are going on in the higher education in Odisha, I don't expect even the colleges might be getting any fund for procuring chemicals. I think Devashish can give me some idea that they're getting really some fund for making laboratory or actually purchasing chemicals.
Okay, let us not stretch this discussion too far because they are very sensitive discussions. I am always hopeful, Paritosh. I'm
Yeah,
always
sir,
hopeful.
that is why I'm we have worked towards a longer run.
Yes,
I think we have to wait little bit.
Yes, we never thought of ever having an NMR equipment in Ravenshaw University.
Yes, yes.
Right? And they are so, see, BSUT has an auditorium, they have a screen which costs is 40 lakhs. We never thought about it. They look like movie halls, right? So things are changing, the infrastructure is changing, only manpower is lacking, I think. Money is not a problem. I think money is not a problem with the government. Only if they properly staff our colleges, things will move. So things are changing. Already it is changing, and let us not be, disheartened what I shared about it. There is a little bit, people are there. Like there is no justification in attending a meeting. It doesn't prevent anybody from attending a meeting or saying a few words. So those kind of things I am talking. It's a kind of mindset which does not require any money or any initiative by any organization or any government. It has to be spontaneous, has to come from within. So this is the thing. Only if Madam is listening to me, and she is a very busy lady. She has a lot of work, but she has attended both the days, even if it is for a short duration, 1 hour, but she could find time. Professor Ashok Mishra is a very busy man, I know, but has been all present for the last 2 days. So it's mindset. I think many things can be changed if we just love our state and love our chemistry and work towards. Thank you, sir. I think I said enough.
So shall I sort of summarize this
Yes, sir.
now?
Yes.
Let me try to summarize as briefly as possible. Whatever we discussed yesterday was extended further in some sense today on some aspects. The extensions were, for example, towards getting the everything video recorded and sort of populating OCS website in such a way that it can be accessed by others and so on. With regard to collection of funds and making it possible for the mobility of students and scholars, that was also reinforced today in different ways. The new ideas that came up are number one is some sort of creating an alumni connect. What Professor Vishma initially started and Paritosh sort of reinforced it. It is actually possible, and come to think of it, I come from Titlanad College, and last time I went to Titlanad College was some 20 years back. So I think it is true in almost everywhere. If OCS members are there in different colleges, I think OCS can catalyze it. Yeah.
Just a minute, sir. In this regard, I am requesting all the professors and scientists who are working outside Orissa.
Yeah.
So anytime if you are coming to your hometown, so at least you give a mail to OCS, and also on behalf of VSSUT also I am requesting, if anytime you are coming to this site, you give us a mail, and we will definitely arrange a seminar or even if extended lecture series in our part. At least I'm assuring that for Sambalpur University and VSSUT, we will definitely arrange workshop or you can say seminar or conference for 1 day, so that our students will be benefited. And at the same time, even if I will be not in the secretary of OCS, so I will request all the next secretary, so that whenever any professors or a scientist or researcher, particularly the Odia people who are working outside, if they are coming to either hometown or even if for any examination purpose they are coming to Odisha, at least drop a mail to OCS, so that we will communicate to different colleges. And if possible, I think if not 100 out of 100, at least 2 colleges will be interested to organize such type of talks. Thank you.
Thanks, Professor Peeraj. And the idea is actually we need a catalyst somewhere. See, for example, I am not going to Titlanad College, let us say, or Professor Vishma is not going to his college because there is nobody there. There is nobody there whom we can go. I mean, it's a little difficult to go and introduce yourself. Say, I was here 20 years back. Please accept me. Please let me talk to you. It's not possible. We need a catalyst. We need somebody who can connect us. And that is a place where OCS can really play a good role. So I'm recording it now. Now I will put it in our summary. So that is a new concept that came up today, which was not there. And Professor Narayan Pradhan's idea of literature update as a service that many of us can do. People in better places have sort of fairly good access to collecting literature, various we have our libraries stocked with all this and so on. We have access to all this. So this can be made as a support to people who need on a topic-based kind of a thing. That will help really. And video recording, etc. we have already discussed. Somewhere OCS can take care of probably hosting them, but recording has to be done elsewhere. Professor Das's, Nigamananda Das' idea of project component of this thing that is now taken care in a sense. It is just that OCS can probably facilitate it as much as possible. The other thing is project writing by honor students. If there can be some broad guidelines and formats that can be made available, so that there is a, if they know what to write, how to write, they will write properly. But right now probably they don't even know what to write and how to write. If some of the senior teachers of OCS can help them in that, that will be a good idea. Then I think these were the new things that came up today.
Professor Patel, is he still there?
Yeah, I'm here. I'm there.
So if I'm missing out on anything, please let me know.
Yes, that's what Professor Misra is asking. Any point is missed?
So a lot of things were already discussed yesterday, and that it got a little extended and reinforced today. On top of it, the new ones are something I was trying to elaborate. Anything else that we should be doing?
Sir, I will ask you, what is your personal...
Actually, what has happened is my personal things are already there in it. Somewhere or other, I managed to get them in.
Thank you.
Yeah. So
I think what I would suggest is, if all of you are listening, please write down what you said. Sir, Professor Misra has recorded, but still you write an email to him narrating what you wanted to say, and then all these things, if Professor Misra has already compiled, and we shall put it in our website. We shall, after compilation, who said what are suggestions.
Sir, actually, one problem will be I have not recorded like who said what really. For me, persons are not important. The concepts are important. So
I mean, the concepts are there. We could just summarize all the concepts and put it for further discussion. And whatever that is doable will be done. As regards to video editing and putting it up, they sound very good. Like suppose I go to a senior professor who is a retired man and ask him to say teach thermodynamics in 10 classes, 10 video clippings. How practical it is. It sounds very good, but to transfer it to practical reality, it is tough, because to prepare a PowerPoint file with the details of mathematical equations and explaining them, stretching over several months, some recording those things, they are really, some kind of money is required, sir, unless you give some incentive to a retired person. It's always some incentive works. So that's what I'm thinking. We shall write to World Bank with that suggestion. Some kind of funding is required, sir, to prepare. I think government has already the provision. We have to pay to the person who is giving us the lecture. Knowledge cannot be. It's good that if somebody does it free, but it's always difficult. I know.
Sir, one small problem may be there in that we have to partner with some existing academic institutions for many of this, because funding may not come directly to us.
Yes, of course.
But we can partner. We can partner them, and funding can come.
Yes, sir. Through this university, Ravenshaw University, Paul University, all universities.
Any university which is ready to take it up.
Yes.
We can partner with them, and the fund can come there, and we can.
Sir, that is the reason why I was saying about the MOU. Even if we can start with, let's say, Utkal University, Ravensa University, so that will give actually a certification that we are partnering with this organization, so that in future
That
also you
won't
can
be a big
conduct the
problem. That won't be a big problem. We have to change the bylaw. We have to
Okay.
introduce some law in our statutes. That is noted. Yes, we can do that. It has to be the resolution has to be passed in the general body meeting.
Okay.
Anything
No,
we do is bound by.
what I said, it may take 3 years also, but this is a path which is.
It won't take 3 years. It's just 1 year. It will be enough, not 3 years. One meeting will be enough. It's not a very big deal. Sir,
so thanks a lot to all the.
I want to say a lot of NPTEL courses are there, so students should be make aware of the NPTEL course, because a lot of good courses are there, like organic reagent, pericyclic reaction. The student, if they can go through those courses, they will definitely benefit. They where to get, how to find this thing. If there's so much teachers in the college guide them where to find those courses, so that will be quite useful.
I think these days the students are very smart. I went several times. I go to Ravensa College. I interact with the students quietly. Most of the faculty, they don't know. I just catch hold of a boy or a girl and ask them, who chemistry students. They're very smart. They're not. Sometimes some students say that it's not necessary to go to the class. Wikipedia and a lot of free PDF files and movies are available.
Especially by the MHRD has developed.
Yes. So they are smart, but all at the end of the day, nothing like classroom teaching. Nothing like classroom teaching. So that is a very big problem now in our state. Ravensa is fortunate to have 50% of the required faculty. Utkal has around 90% of the required faculty. But what about other places? 1% in Khalikot College.
No, sir, we are less than 1/3.
You not even 50%. See, that is the problem, sir. So if the teachers are not there, Ravensa College, when I was there, we were 26 faculty members. We had freedom to teach, do research, and also help in administration.
I am alone in Dhenkanal College.
You are head of the department and plus two and plus three, one man. He is the only. And he's very active, and the principal is heavily dependent on him for most of the administrative work. So that is a serious problem. Government has started building of the institutes in terms of infrastructure, and they're seriously trying to address this manpower issue. A lot of efforts are going on, and Shruti knows better that in the part of the government now, maybe within a couple of years, they are trying to fill up most of the teaching positions, right? Right, Shruti?
That is insider information.
We are trying, but we don't know how far will be fruitful.
Sir, can I tell something, sir?
Yes,
sir. Actually, problem government is giving money, but they don't know where to spend and where not to. They are spending money on buildings, but they don't give for equipments or chemicals. So, chemical society has the role here to place before government. What is more important for the institution?
You don't have to ask chemical society. Just ask Smriti madam. She has a strong connection. She can tell what exactly.
No, sir, that is not the truth.
Anyway,
actually, they will have to contact their principal, because how the budget is done, according to that, always the funding comes.
Madam, shunantu. Aguru amar problem kichi thila ki amaro.
Nobody asking now the principal.
Devasis
are not involved.
Aguru amaro when my college days and in our college everything was defined. Everything was defined. How much chemical, how much if college gets this much of money, chemistry department gets 55%. Everything was defined. Geology, actually one chunk of money comes and it is divided among the departments. Now I think money is coming because I was principal in government.
Bonta utla equally कार जितनी requirement अच्छी से अनुसारे इधर से होनी.
Thank you.
It depends upon the authority always.
My goodness, That is dangerous.
Sir,
Because
Chemistry
money
requires
is
a lot of
coming. Money
consumable.
is coming.
Yes.
I'm not saying that with the connection in the government. I'm saying that with the connection in the university, because
Yes.
I know now what is happening.
That should not happen. It's a consumable. Chemistry is a consuming department. We have a lot of consumables. Physics is a doesn't have that much of consumables.
They will get one time. They will get one
can
time
I tell you
allotment.
something here? Sir, actually, I am telling that government don't know what we require. Last few years, government is providing money for equipments, but they don't know chemistry department requires chemicals and solvent. And as per our accounting section, we cannot spend money of the equipment in the chemicals. For that, I have then contacted the then deputy director who was a chemistry man and approached him that sir kindly tell government that chemistry department needs some chemicals. After that, the deputy secretary changed the law and give some allow us to purchase chemical from that fund. So that is a
That's
problem.
why I'm saying you will have to be proactive. Otherwise nothing will happen. Whatever you need, you will have to present that. Then only anything can happen.
But government have to also give the scope to us.
Who is there in the government and who is the government? There are some officers.
See, as I think this panel has something else to think. This is one thing. This kind of problems, Professor Misra might not have experienced in IIT.
No, I know very well.
So he's remaining quietly and listening to us. This is a
no, my task is over. I've actually handed over to you.
Okay. So I now request the convener to propose a vote of thanks to the chairperson of this panel and all the panel members.
Thank you, sir, Professor Misra, sir. It's a nice, innovative idea by OCS to introduce the panel discussion. And first time probably we heard about it, and a lot of lot of things have been discussed, and I wish it will have some result finally. Thank you, Professor Misra, and the panelists, Professor Das, Professor S.K. Swami, Professor Paltosh Mohanty, Professor Naran Pradhan, Professor Nigananda Das,
Professor Vishnu Patel,
Professor Bhishma Patel, and all other participants. Thank you very much for nice panel discussion. Now, the panel discussion has been come to an end, also our conference. So I am again thanking Orissa Chemical Society,
We shall have
the
concluding session. There is one more session. Please go through the, we have a closing function. And in this closing function, let me see. We have a closing function and I have to make a brief remark. Dear friends, I think this is the first time that OCS has ventured into such kind of programs. So since it is for the first time, we might have committed a lot of mistakes. I am sure about it. And one good thing that has happened is that OCS has agreed to conduct this kind of meetings time and again, not only with the academia, but also with industries. We have a lot of industry in our state, and some of the industries have R&D facility. And we shall be having very shortly another seminar this month, in month of December, OCS industry webinar, where we have a lot of speakers who have done good research, industrial scale research. They are solving their own industrial problems. So the idea is that to acquaint our students to choose industry as a career. This idea of this meeting was to choose a chemistry research as a career. So we do not know to what extent we have influenced our students. Kindly go back as emissaries and wherever there is a chance or a scope to influence our students, do it and tell them in black and white that there is nothing like choosing chemistry as a career. It is a real bread earner. It can provide immense satisfaction and opportunity throughout life to do innovative research. There are a couple of other seminars, and probably we are looking at some kind of specialized laboratory work. Like suppose we have in our state a laboratory which is doing some kind of innovative research. We would like to have a one-day seminar on such themes, such in those laboratories, to encourage the PIs, those who have started that kind of work. Certainly we shall be deciding in our state, in our universities, identify like research centers, like those who have made significant contribution or publishing good quality papers, some new kind of work to encourage the PIs. It is another dimension which OCS is thinking of, which will be coming up very shortly. And lastly, regarding the curriculum, the OCS has a vision of putting equal emphasis on teaching and research, so that teaching part involves curriculum, this practicals and all that. And probably Professor Sarat Kumar Swai will come forward. Professor Swai will come forward for that curriculum meeting. We can have one webinar where we shall put all these things in right perspective and discuss and decide what is to remain in undergraduate level, what is to be in postgraduate level, and regarding those practicals and all that. So, sir, the point is OCS is a kind of state level body, but our manpower is very much limited. One president, a few members, and secretary, and so we have, apart from our society jobs, any new job requires your cooperation. It is not possible that we can be successful. Like myself and secretary and a couple of other active guys cannot change things. We're trying our best, so let us all join hands. Wherever you are, if you are thinking for the state, please give some time, and anytime all of you are requested to reach us through email, through telephone call, instruct us, guide us, tell us what to do, and we shall be more than obliged to respond to you. With these words, I thank once again all of you for kindly sparing your very valuable time. This is a Sunday, and I'm standing between your lunch and this meeting. I thank all the organizers in the local organizing committee, Dr. Mohanty, and also I thank Professor Mahapatra, OCS secretary. He has done excellent job in 1 year time, even if we have this corona pandemic. And I really thank you all. Without you, the dignitaries, the members, OCS doesn't have any standing. So Professor Misra, Professor Mohanty, Professor Pradhan, your number is very small, very small. In Orissa, I mean, that is why you are very important, because you are very few in number. That's why you are very, very important. You have a very crucial role to play for the state. This state is our chemistry is our growth is kind of, I put it like it's a kind of Darwinian kind of growth, very slow, just like your evolution. Our evolution is very slow. Nevertheless, it is positive. It is always going for the better. Things are changing, and why we should not suspect OCS or Orissa is that anybody who is going out of Orissa is excelling. Anybody is going out of Orissa, mostly they're excelling. That means Odia people, there is nothing wrong with Odia people. there is something wrong inside the management of these talents. So I am always hopeful that if we properly look back and go back to our school from where we came and try to uh, just give whatever input you have, the way encouraging words you said will go in a long way in changing this state within a decade or so. With these words, I thank you once again, and I now request Professor Mahapatra to propose a vote of thanks. When there is an announcement to be made by OCS about next events, and then Dr. Mohanty, convener, will propose a vote of thanks. So first, Dr. Mahapatra, you have something to announce regarding what will be the next event. Are you there?
Yes, sir. Yes, sir.
Yes, go ahead, please.
So next month we are planning to have a OCS industry meet, and next month means day of the January, VSSUT is having an OCS extended lecture series and a national conference in recent advancement in material science. So we are going to organize it, and I need the support from all the participants and all the resource persons, and particularly the panel members. Your guidance and encouragement is very much important to us, and we'll definitely in touch with you. And very shortly, we are giving you the circular, and this will be the OCS second extended lecture series on material science. And I have also requested some of the colleges to organize such events, and if they will write to us, then immediately we will inform all of you, so that you may be one of the resource person, and you can help students who are not able to attend all these seminars and conferences, but particularly the peripheral colleges. And your help will be very much essential. Your words and your guidance is very much essential for those students who are not privileged enough to attend the such PG centers or universities. They are in the interior colleges. And I thank you. I thank all of you for your kind cooperation. Thank you.
Now, Dr. Mohanty, before you propose a vote of thanks, I would like to remind you that there are many senior teachers still in listening to us, and please reach out to everybody and propose a vote of thanks. Dr. Mohanty, please.
Respected President OCS, Professor Samal, Secretary, Professor Misra, Professor Patel, and all the senior members and teachers, past presidents of OCS, the speakers, and the participants. First of all, I thank this pandemic because it gave us a scope to organize this virtual meeting in which we got participants from all over the world, because a small place like Dhenkanal cannot get so many persons in physical mode. So we are very excited and by organizing this conference, and we are very much inspired by all the talks all presented here. So therefore I thank OCS, Orissa Chemical Society, the President Orissa Chemical Society, the Secretary Orissa Chemical Society, for giving us the opportunity to conduct the first extended lecture series of OCS. I am very much thankful to past presidents of OCS, all the members of OCS. They are present throughout the conference and encourage us to do better in future. I am thankful to all the chairpersons, Professor Subhasini Lenka, Professor Satyaban Jena, Professor Vijay Misra, Professor Bhishma Patel sir, for chairing the technical sessions. And I am very much thankful and express my gratitude to Professor Ashok Kumar Misra sir, who has throughout the 2-day session and very nicely managed the panel discussion and give very much inputs to us. I am thankful to all the speakers who have spent their valuable time to told about the recent advances in chemistry, and to all the participants across the country and some from outside, so that without them the conference would not be much successful. Now I want to thank my principal, Professor Dr. Asmi Misra, who is a very dynamic leader. Without his guidance, we were not able to organize such a conference. I am also thankful to my colleague Dilip Kumar Naik, Assistant Professor in Computer Science, and Rajnikant Khuntia, Assistant Professor in Commerce. They have supported me throughout this program. I am also thankful to Bigyan Jali of BSSUT. He has also put many effort to organize this conference. I am again thanking you all. Thank you. I hope you have enjoyed the conference, and you should give the feedback in the feedback form so that we will improve in future. And I apologize for any wrong have been occurred in during the program. Thank you all. Thank you.
The meeting is over. Thank you, gentlemen, ladies. The meeting is over. So wish Devasys there should have been a lunch after this.
We'll remember him when we take our lunch.
The launch will be also virtual, sir.
Virtual lunch. We are all so hungry. So fantastic. Really, I think after this, even the real in-person meetings are initiated, we should continue this virtual meeting primarily because it is we don't have to spend money and get excellent speakers from anywhere in the world. So
this is here to stay. This particular mode is here to stay. It's not going to go